You see that?
Yeah, but how many? Yeah, okay. Yeah, fine. Yeah. Good.
Right, we start. Good morning, everyone.
Good
So
morning.
it's a pleasure to introduce you to Vincenzo Innocente, who has been working on software for the past 90 years.
90.
No, yes, if you integrate all the work that he has done, maybe also 100. So today it's a full day on floating point computations. You say, yeah, what's the problem with floats? You will find out.
Maybe.
Maybe.
Maybe you already know.
Okay, we can start. Unless there are any general questions. No. Okay.
Welcome. My understanding is that now you are master of C++, whatever it means, okay? Well, floating points can be used in C++, but actually in any other language. So floating point arithmetic for scientists, where here with scientists, we don't mean computing scientists, even though a lot of what I will say usually targets to computing scientists. The same course for computing scientists is 4 days, the same topics. If you are interested, I can forward a very recent course for computing scientists on the same argument, but some, because the fourth module usually is not covered, which is the part of efficiency. So what we will cover is precision and accuracy, and then also efficiency. I think that during the previous 3 days, you have done a lot of efficiency of computation. So many, so if you want, you can use some of the tools you have learned yesterday, last days, few days, also with the exercise we will propose during the day. Let's okay, let's try to start. What's a floating point? So, in science, we make measurements, right? And the result of a measurement, whatever people say, is a rational number. You cannot say that the result of your measurement is pi. Maybe it's 1.5 pi, but still your result is 1.5, it's not pi. So for instance, the mass of the X is 125.4 GV plus minus 0.12. But we see, first of all, that this number can be represented by an integer. Name EV would be an excellent integer. And as you notice there, the error is 0.12, which is already like 0.1 would be enough. Yeah, and the mass is, of course, published with just the same precision, we say, the same number of significant digits. Remember this word, precision, significance. There's the error. So we can use integer. Well, it does happen that we use programs which are very generic, like Gen4, right? Which is used to track particle in thin foil of oil, of gold, say 10 micron, or in the interstellar medium. Both the density and the distance is much larger. For instance, the mass of the X is a mass you expect to be expressed in SI units. In SI units, it reads as 2.2290 for 10 to the minus 25 plus minus 2.1 10 to the minus 28 kilos. If you want to represent both the two numbers, or if you want to represent the mass of the sun and the mass of the X for the same generic program, well, integer won't work anymore unless you are not so bold to use a variable number of digits, and it exists programs which can work with integer of 2000 number, whatever. It takes a little bit of space and time to do the computation, but can be done. So all this you have learned most probably undergraduate school or even at high school, and the thought these are just scientific notation, and floating point is just a way to represent rational numbers, because 1.5.04 is a rational number, 2.229 10 to the is a rational number. It's not. Any number we write is a rational number by a fixed number of digits, which usually is also called the precision. Okay, we will discuss this, but the number of significant digits is usually called precision, although it's not the precision, right? Multiplied by a base, in this case is 10, with an exponent. So 31 times 10 to the minus 1 is a floating point in base 10 with a precision 2. So yes, 2 significant digits, 3, 1, 31. And it's printed in decimal. Let's distinguish how we print a number, how this is represented. Now, something important is that usually floating points are normalized, which means that the first digit is always non-zero. Okay, so this number we don't write as 0.031 10 to the 3, although we can write it as 3.1, and in the following I will take the freedom to write it as 3.1. 1 point, all that, fine, I will not read it, is a floating point in base 2 with the precision 24, printed in binary. Now this is very nice, the binary, because if the first digit is not 0, it can only be 1. So if you say that a number with precision 24, okay, is normalized, but you know that the first digit is 1. So you only need 23 bits to represent it. Of course, we will not, nobody writes a binary number like this in binary. Usually you use the hexadecimal form, which is this one. 1.921FB6. If you check, this corresponds, this one is 9, this is the problem is that here you have only 3 digits, which implies that this, instead of being 3, is 6, because there is an additional 0. So if when we print a floating point, so this is in base 2, precision 24, which is will always be even, but the last 0 is not in the number, is 1 more bit, which is not bad, we see. Okay? This, I suppose that more or less you have at least have seen this already once in your life. Now, there are some very trivial properties of a floating point, right? So first of all, they are finite, and there are always a previous and the next. And in particular, so the previous number of 31 is 30, and the next one is 32. There is also something interesting that if you look to any of this number, like this or like that, if essentially they are ordered, they are strictly ordered, and they are strictly ordered with their integer representation. Include whatever way you do it. So the previous of 1.921 FB6 is of course before. Remember that the 5 doesn't exist. And the next one is 8. Now, the difference between 2 consecutive floating points is called ULP, is the unit in last place. Okay, so the difference between this one and that one, which happen to be 2 to the minus 22, because this is yeah, is called the unit in last place. And as I said, okay, there is in general, this is correct. For each value, I have not yet, for each value of the exponent, there is a finite number of floating points, and this number is always the same. So in decimal are 99. Sorry, it's not 99, it's 89, because 101 is not, is actually 10 of 10 times 10 to the e minus 1. So it's not in that, in the same order of magnitude, if you wish. It's called, in binary, it's easy, we call it a binate. Now I call also for this one binate, okay? So this is the binate in binary. Any number larger than this will become, so then the next to this one is 1.02 to the plus 1. The previous one, this is 1.5 e to the 2 to the e minus 1. Sound?
That X representation that you have there, should the last digit be E instead of F? As you mentioned, it's always, no, down. Yes, F, E is F.
No, it cannot be E, because E is odd and it's not base 24, otherwise would be base 25, okay? So you said it should be E. Yes, you're right. It's right, good, you got 1 point, 1 mark. Mark, he has already got 1 point. You had the same point? No, it's a different.
The third line, I didn't understand why 5 and 7 are not.
Yes, this is because the way in which we represent floating point with the 24 bits, because the 1 is back, so we have only 23 bits. And as you know, so what I said in the slide before here, the number is this one in reality, okay? But because 6, you see 0, 1, 1, 0. That's 6. But then the previous of this is 0, 1, 0, which is F4. Okay, and the next one is 1, 0, 0, which is F8. Okay, so there is always a, and as you notice, this one is not correct. It cannot be F, it's E. Okay, and so you already passed the exam. You should not come to the floating point exam. And how could be? I mean, this was charged fully. I changed the batteries. Okay, this is the most important slide of our course. After this one, you can also go. Okay. All right. So let's say from now on, some of you have recognized pi in the number we had before. So let's say that the result of a measure is 3.1415. But its accuracy is only 0.1. Okay, so you will not publish 3.1415. You should publish 3.1. You should round it, right? So 3.1415 rounds to 3.1. And as you have learned at high school, 3.1515 rounds at 3.2. It's okay. So you understand rounding. Good. So now we have these floating points, which we said is only 24-bit precision. So the number I wrote before, which is 1.921 FB6 2 to the plus 1, which if you print it using X floats, it reads this string here, which will is 3.14159274. Okay, that's the rational number written in decimal. So this is the same number. One is written in decimal and the other is written in X. Good. Now, the previous one is this one. The next one is this other one. In C, C++, whatever, the standard, the function to get the previous order number, next one is next after, and with the direction. Usually you can use inf. That works always. Okay, and now comes the af, because we can use the af. This is the midpoint between these two. Okay, it cannot be represented. It doesn't exist, but it's useful because that's a rounding bit. Now, it happens that the real number pi, this one, sits here. Okay? Now, so this number is not just pi. It's any number, rational, real, whatever, between this one and that one. Precisely, yeah? So you take this as a rational number, this one as a rational number. All numbers between these two are represented by this. Okay? Between all those numbers happen to be pi, which sits also in a very bad place. So there are three reasons why this is bad. First of all, you notice that it's closer to the midpoint that its number it represents. Second, is represented by an odd number. And we will see that odd numbers have some strange things. And third, this number is larger than pi, which makes some people a bit odd. Because nervous. Because if you have something like ACOS, this is defined between minus pi and pi. So they don't like that ACOS minus 1 to be this number, because it's larger than pi. Okay, and you can go to the source code of ACOS for Apple. So if you say Apple Math is Apple Math ACOS, and you will read why you will return this number and not that number. But this is only because of that one. Okay, fine. This is just for the fun of the floating point numbers. Okay, so this number represents all the real number in this interval, between the two midpoints. Okay, this is the ULP, this is the ULP. Now, again, what's the precision of a floating point number? So, most part at say undergraduate or even in high school, you have learned to measure something with the ruler. So what's the precision of the ruler that you have learned as a measurement? What's the precision? Come on. Yes and no. Who would say something different?
I was just going to say the smallest increment that's given by the...
Yeah, the thick, what is called, yeah. We usually say it's aphatic. Huh? Maybe it's aphatic. And if you are, and because we sum the error in Gaussian, when we can even divide the thick by square root of 12. Yeah, we physicists are crazy. So we say that so when we write this, oh, this is 3.55 centimeter plus or minus 0.1 over square root of 12. But no, forget about this. So yeah, so let's say that the precision is half a ULP, but or one half a ULP. So this is because essentially we say that the number is correctly rounded if because essentially what we say that pi is correctly rounded if is this number. So means that if when you do a calculation, no matter how many digits, if it's between this and that. So because as we said that this number represents all the real numbers between these two. So this is a full interval, but it's centered around here. So it's like saying that it's 3.5 plus minus 0.5. 0.05. Okay, anyhow, so far for the ruler. That's that. We can put the ruler there. So now, here we have done this rounding, but there are many other ways of doing rounding. Okay, so there are 6. There is even one more, which I love, which in the direct round there is a fundamental one, which so the rounding, the default rounding is called round to nearest tie to even. What does it mean, tie to even? Well, that for instance, if you take the difference of two numbers between in the same binate, half of the one is odd, one is even, it will end up in the midpoint. Obviously, I will do it in decimal. It's obvious, right? In the midpoint. So if a number is exactly this, how you round it? You round it to even. So this number can never be the result of the rounding of a result which is precisely in the midpoint. It will go either there or there. So if the result is exactly in the midpoint, it will go to even, which makes such that they are uniform. Because sometimes it's less, sometimes it's more. The other possibilities is that he round to nearest, but when it ties, it always go away from 0. So if you have positive and negative, it will be uniform, but in reality it's biased. Of course, you can do round to nearest tie towards, but this is not defined. And then you have the direct rounding. And the direct rounding, besides the okay, this one is already over. Great, this point. Do we have a pointer? No. We have the ruler. And usual, and I'm not high enough, so I have to go close. And so we have 3 rounding, okay, which is towards 0. And this is direct, so you always go towards 0. And this is symmetric, is mirror symmetric. And then toward infinity and toward minus infinity. Now, these two are useful for interval arithmetics, if you have it there to do interval arithmetics, because it will always round to back and to last. But if you want to use it for any reason to verify your computation in any program you write, it will break up, because the probability that you assumed mirror symmetry, I mean that the sign of x is equal to minus the sign of minus x, or that the forward calorimeter, the backward calorimeter are mirror exactly, this one will break, okay? So don't expect that a program written by an engineer, somebody with conscious engineer or physicist would never work if you do this. While this other one, it gives some bias. There is, of course, a direct rounding away from 0, which is also of interest. And in fact, I think has been introduced. So these are the rounding modes. Now, as I said, a function, we say, remember, a function, so a cos d minus 1, is correctly rounded if the result corresponds to the result rounded true value, right? So if a function has to give pi and it gives this number, is correctly rounded. Okay, if it gives this one of that one, it's not correctly rounded. On the other hand, we say that it's faithfully rounded if the result corresponds to the one on the 2 closest FP numbers to the true value. So if you have a function which the correct result is pi, but it gives any number between these two, so I mean these are floating points, so FB4, FB6 or FB8, that's okay, it's faithfully rounded, right? It makes a huge difference because of this midpoint. Having a function faithfully rounded is almost trivial. Having a function correctly rounded takes ages. We will see, maybe. Okay, now, all what I said previously is generic mathematics. Okay, it's nothing to do with computing, even though it's been developed, of course, but no, it's even not. I mean, it's anything that if you have trigonometric tables, you most probably when you were born, trigonometric tables were not even more printed. Okay, it applies to trigonometry. So FP always treated to perform arithmetic computing. Okay, so since 1985, so it's been the 40th anniversary of IEEE 754. This is the operation of between floating points are standardized by the standard that and you get, and if you type IEEE 754 on Google or whatever, it will give you infinite amount of as we speak, there is no, starting tomorrow, there is ARIT 26, which is the IEEE arithmetic conference, and which we start, and this is at 26th instance. So the standard defines the formats for both binary and now also decimal. And the format consists of a finite number, usually 16, 32 bits, I mean, you don't go, including some strange objects like the sign 0, and the subnormal numbers we will see, infinities, and a special number which is not a number, which is, for instance, what's the result of square root of minus 2. Square root of minus 2 is minus none. Remember this? Remember this?
What is a subnormal number?
Yes, we'll see in the next slide. Thank you. Excellent question. It defines also some interchange formats, means that formats that you can represent, you can store, but when you want to make arithmetics, the arithmetics is not defined by the standard, you have to convert to one of the arithmetic formats. And then, of course, the rounding rule we have seen, and then the operations, standard operation, plus a whole set of what they call other operation in the standard. So the standard usually you cannot access because it's protected. In reality, any version prior to the published one is accessible. Usually is, and if you don't find it, I can give you because I am on the list and I receive each new draft each second week. So they define trigonometric operation and so on. And then a whole set of exceptions that we will not cover because they are a pain and they are usually very difficult to trap. Also because once you are trapped, you are doomed. The only things you can do is exit, as you have learned. That you have learned that on Linux there's no chance to recover from an exception. In any case, you don't know. I mean, who right? Because it will. Okay, you have done yesterday, right? You know everything about C++ exception, and the probabilities that is correct is 0 because I mean, you have to. Now we can discuss this. So here we go, the floating point representation. So this is all the floating point representation. This is actually the encoding. It's half, single, double, the x86 extended. That's in say, now it's not used. No, it's still there because, of course, any program of the 70s is still running properly on your laptop, and so they were using x86 extended form, quadruple and octuple format. So this is our nice fraction that we have already seen. The only difference with respect to everything I've told is that the exponent is finite. Before, we have just mathematics. The exponent could be any number. No, here the exponent is finite. Okay, so because we have 32-bit. Okay, so the single precision, which is the one I have used before, with which is precision 24. But as we said, if it's normalized, the 1 is not needed because we know it's 1. Okay, and as the exponent is 8-bit. Okay, and then there is the sign. Good. So this number is the sign. The this is called significant. In Aborigine was called the mantissa. Now you will excuse me if sometimes I will call it significant, which is correct. Some other time I say mantissa, right? So this, the red part is the significant, and which has the implicit one. And then, of course, the exponent. The exponent is biased. So you read a number, you subtract 127 to get the correct one. Okay? Fine. And this is so this number is 15,625. This is copied from Wikipedia, and you will find in any slide on floating points, always the same figure coming from Wikipedia. For the rest, it's here. Okay, good. So usually this is single. Today we will work with single because it's simpler, also because we see what happens, and he has only 6 hexadecimal number to look at. If it's in double precision, there are 53 bits, which, I mean, doing an exercise, something more that on a modern computing, you can essentially scan the whole single precision in nothing, a couple of minutes, seconds. Again.
Because I'm a bit lost. So the
Okay, restart. We'll restart.
the sign.
The sign is the first bit and is to the whole number.
And if it was plus, it was 1.
No, it's 0, it's plus.
But then there is, I'm not understand why there is -1.
Because -1 to the 0 is 1. Good. -1 to the 1 is, yeah, it's a funny way to write, but what I can do?
And,
Ask Wikipedia.
okay, and then the last thing that I didn't understand, one of the other things that I didn't understand, the x minus 127.
X minus, yes. So this is the exponent. Okay, the exponent is 8 bits,
Yes.
but it's positive. In order to represent a number which are below 1, we need a negative 1. So what you read here is the exponent plus 127. We'll see maybe in some slide after, okay? So you have the exponent, you subtract 127, and you get to the real exponent.
Okay, and which is the meaning of x?
Of x here.
No, it's,
This is the exponent. I don't know why it's x. It's this number. Maybe I have to put it green here and red here. M is this one, x is this one. Okay? This is, again, okay? Okay, so maybe here is better. Comes always from the same page of Wikipedia. Okay, now, so as we say, this is a normalized number. Okay, so all the number which we use. Okay, so is the sign bits times 2 to the exponent minus 127, and then multiplied by the mantissa, which is 1 point and all the bits. Now you notice that now if the exponent is 0, what we do? Well, if also the significant is 0, this is 0. Okay? So 0 is 0. Integer floating point is 0. Now you say, oh, but the sign bit can be 1. Yes, this is -0. The infamous by how useful is -0? Complex number. Right? Complex. You know the cut on the negative axis of a trigonometric function? Come on, come on, come on. You are either engineer or physical computer sciences. You should know how to do. You should know what is the cut on the negative numbers for hyperbolic function, right? Of course you know. Okay, so yes. That's the only use I ever seen of minus 0. Okay, but anyhow, so if the significant is not 0, these are the famous subnormal numbers. So are numbers which are smaller than the smallest normalized value, right? Because this here is 0, we see some example, and then so this number actually is below 1 to the 27. Okay, so is this. Now you say, why not 0? The problem is that if we don't have subnormal numbers, then any operation between numbers which are very small will be not correct. It will go to 0. Okay? If you do the difference between two very small numbers, 2 to the minus 27, 20, this will go to, the result is 0. Instead, it can be subnormal. And this can be useful, we see. Okay? So, so subnormal numbers are useful in order to make the very small normal number useful. Otherwise, they would be not useful. Now say, I don't care. Yes, in fact, most of the in the cases, you just forget about subnormal numbers. See, and only in the last 5-10 years, the hardware supports subnormal numbers. Before, they were just switching to software, and it will take forever to compute. Okay. If the exponent is all ones, this is infinite, represent infinite. And if the significant is non-zero, it represents a none. Come on. Sorry. So let's see. So this is how they look like. 0 is 0. 0.5, which is 0, 1, is this number. Okay? Say it's all 0. Yes, it's 1.0. 0.5. Any power of 2 will all have the significant 0, right? It's 1.0000 times 2 to the minus 1 to the 0. 1.5 is a power of 2, 1.5? No. And in fact, he has a 1 in first position. But that's it, right? You see it? Okay? So it's 1.10 to the same power than 1. They are in the same binate. 1 and 1.5 are in the same binate. Have the same power of 2, right? All the numbers between 1 and 2 are the same magnitude, have the same exponent of 2, right? So between 1, 1.5, up to 2 minus its own ULP, which is 2 to the minus 23. Okay, 2. Again, it's changed just the exponent, right? To get that exponent, you have to subtract 2.538. Our infamous pi, which now you know is not pi, is this number. You have already seen it. You recognize it. This is the best number we can ever have. This is 0.1. 0.1 is this number. It cannot be represented as a rational number in base 2. Huh? Like 1/3. Come on, you know, from primary school. How they're called in primary school, the number which is 0.3333. They had the name. Huh? Periodic number. So this is, so 0.1 is a periodic number in binary, also 0.3. Okay. This guy is the smallest number which can be represented as a normal number. Okay, so he has all zeros but still 1 in the exponent. So this is the smallest normalized number. This is the largest normalized number. It's all ones and the exponent is almost all 1. Okay, you add 1 and this becomes infinite, but you don't add 1. You add 1 ULP of this number. If you add 1, we will see it in next slide. This is none. It's not 0. The 1 usually is not here. It could be there. This is infinite. This is 1. This is none. The significant is non-zero. This is infinite. The significant is 0. And this one has all the exponent 0 and there's something in the significant. So it's subnormal. So this is a subnormal number. You see, the exponent is smaller than the 26. Okay? If it was 1, it would have been under 27. Right? Yes?
How does infinity look like?
We have seen it. Oh, he has 0 instead of minus. Sorry. You can have also minus none. As I said, the result of the square root of minus 2 is minus none. It's not none. The result of 0 over 0 is none. Don't ask me what is the result of minus 0 divided by minus 0, because most probably it's none and not minus none. It's written. Okay. So, as I said, we are on a computer, so we have to use a language. So how they look like, how all these things, you can get it from C++. So if you want, now, I learned C++ before you were born. So I use cout, okay? So if you want to print in hexadecimal, you use the modifier xfloat. If you to write it in scientific notation, you write it in scientific and you can set the precision. If you want the default, which is a 5-digit whatever, this is the default. Now comes the point. So if you have a floating point number and you have seen that you convert to int, you get the rounded version of it. So 3.14 will become 3. 3.7 becomes 4. Or is truncated? No, it's not truncated. Anyhow, if you want to say, but I want the bits. I mean, we have spent almost 1 hour looking to bits. Well, you have to cast it into int. Now, as you have learned, casting is not allowed. There is even undefined behavior. If you have a union with the f float and int, and you write in float and you read from int, that's undefined behavior. It's not. It will always work. It's undefined behavior. So you have to write memcopy. Of course, nobody will call memcopy. He will not call memcopy. He knows that you are actually casting. So, but this is it. Okay, so if to be correct, in C++, in C, you have to memcopy the float into the int. And then you get the representation. Then you print it and you get everything, this wonderful thing. But actually, to get it in, to that, you use bit set. So if you do with the bit set, you get this. Okay? So if you have nothing better, but you want to have 32-bit printed, you use this. If instead you want, as I said, if you want to print it in xfloat, like this, you get that. Okay? Now, if you want the exponent, this piece, well, there are many ways to do it. Okay, everybody has his own preferred way. You shift and you mask. This you know now, but you are a master. If you don't, next week you will do only that, okay? Because on FPGA, you only do this kind of stuff. And you subtract under 27, okay? If you want the significant without the 1, you do this, okay? Without the leading 1. There are also some functions to go back and forth. One is called frexp. The other one is called to go. This will return the exponent and the significant in float, not in integer. So it will return 1 point whatever. And if you have the two numbers and you want to go back, there is something which is called scal bien. You give this the 2, and it gives you back the float. Okay, so, but they are usually slower. This is as you like. Now, everything that you want to know about your type is written in limits. You have seen limits? You have seen already limits. Okay, so these are typically limits. If you say bool alpha, yeah, true, false, or the number will be printed by default. If you put x float, you will see it in x. Okay? Precision, this is epsilon. Yeah, now again, epsilon, what is that? Everybody says, what's the precision of a floating point number? 10 to the minus 7, right? Now, what's that? But depends, you can have two answers. First of all, is the relative error, which is correct. Because, or if you wish, is the ULP of the binade 1 to 2, alias is 2 to the minus 23. Okay, but that's the equivalent of a relative error. Maybe this is something I should discuss a bit more before. I mean, it's clear that the floating points, because of the ULP and the exponent, as a real number, the precision is relative. It's not like the one we have done it. So the precision of 3.14 is 0.01, but the precision 3.14 to 10 to the 6 is 0.01, 10 to the 6. So it's always 0.01 relative, but if you take the ratio, it's 0.01, okay? So floating points are number with a relative precision. Now, you have seen this, you have shown, since 23, you have shown 26, right? So you can have, if you ask STD float, you can say specific, instead of saying float double and whatever, you can use float 16, float 32, float 64. All this is, of course, new and are relevant for machine learning. Okay, so this is more or less the usual table, but if you want, so these were the C language type, and these are always the same, but if you want, we can use float 32 underscore t, float 64 underscore t. If minus std equals C++ 23 or C++ 26, usually this is required. Think the default on GCC now is 23, maybe. Anyhow, if he says he doesn't understand, you write C++. Huh?
20, GCC 16.
So you had to explicitly say 23 or 26. You always you put 26 if he is okay. All right. Yeah.
Here we don't have a bit for a sign.
We
don't have a bit for a sign here.
Oh, it's not written, but yes, it's always there.
Okay, because for precision it's 24 now.
Yeah, because that's the real precision. So you have always to remove 1. Bits, yeah. I mean, the precision is 24, but the significant is 23 bit.
Okay.
I don't know. Yeah.
So when you say leading one, that is that 24. That is all.
Yeah. The precision is 24, but the leading one, we don't care. Of course, in decimal, we cannot do it because it can be any number between 1 and 9. You know? Now you say, but there it says bit of precision 53. Did I type this one? I don't think so. I copied. Better I look where I copied, because you are right. See, there is something that doesn't work. Because either it's 50, 24, and 50. No, maybe no, it's 53. It's doing. No, also here says bit of precision 24. Significant. So, okay. So here you see. Oh, God knows. It's, the other one, I suspect, is the standard. Okay? So the significant is 23 bits. The bit of precision is 24. For double precision, the significant is 22. It's not odd, it's even. Okay? So, Python. Of course, most of you write in Python. So when you say float in Python, it's double. Like in Java, I don't know, in Rust or in Junio what it is, but it's double precision. On the other hand, is this wonderful things that you say .x, and it will print the number in x. So you say float.x or float.from x, and you can convert to and from hexadecimal, which makes life very easy to test what is the floating point representation of pi minus e, for instance, as I had to do this morning. NumPy instead defines float 16, float 64, float 64, and for architecture which supports float under 28, like x86 64, also float under 28. I have not really tested that the sign of it works, but okay. And you just click there and you will see what it is. Python is also wonderful module, which is intrinsic. You don't need to import, which is, well, you need to import, but it's there anyway, which is called decimal. And you will learn after the second line you write that yes, decimal and then capital decimal for the decimal is a module which is providing floating point number in base 10 of arbitrary precision. Why decimal are important? Because as you will see in the anecdotes, most of the financial transactions are broken if you do it in binary. But this is all useful in order to do our exercise and examples, which we'll skip. We continue to the second module because it's more useful. But the break is at 10:30, so we'll do. Also because till now we have just done definition, and in principle this you should have already know. So on the scale of 1 to 10, how likely that this question is using binary? 4. What's the 4? 4 is not a binary number. So, okay, so these are the arithmetics. Okay, so this is the basic, okay? The basic, we want to do arithmetic, fine. We have represented number, but what we do with this number? So what we do with the number is doing arithmetics. Arithmetics means plus and multiplication. All the rest are functions. Okay. Oh, I said there are two basic operations, sum and multiply, right? This is algebra. This is the algebra of the sum. Who is a mathematician here? Who has a degree in mathematics? Oh, shit. All right. Well, who got a course on algebra? All right, or the real algebra, not, I mean, 2.4. Okay, yeah, fine. So, it's actually what it is. So we start with the things which is complicated. So if wherever I write a plus b, wherever I write is not code, a plus b or 8 times b, xb, this is the exact multiplication between a and b. Now comes also the problem of what means exact. I will come later because this is tricky. Okay? It's tricky. If I use this symbol, instead, That's the rounded sum and multiplication between two floating point numbers. And is the result is printed by your program when you say a plus b or 8.b. Okay? This is what you will find on any paper on floating points. I cannot do anything. Okay? These are a plus b, a star b are the corresponding operation in code, at least for C++ and Python. That's correct, right? Fine. Now, in order to do the example, now I don't believe that even me, I'm able to do arithmetics in mind using binaries. So we will use decimal. And we will use decimal with precision 2. Okay? Now, even a kid at high school, at middle school, should be able to do the following, right? I expect so. So everybody should be able to do 42 plus 3.7 with precision 2. So don't say that the answer is 45.7. 45.7 is not a number with precision 2, right? So 42, but is the result of 42 plus 3.7, right? The result of 42 plus 3.7 is indeed 45.7 is the correct result, right? As I said, is the exact sum between A and B, right? So 42 plus 3.7, yes, this is what I had to use. Haha, 42 plus 3.7 is equal 45.7. Is correct? It's correct. I could do so. 42 plus 3.7 is this number correctly rounded, which is 46. Not 46.0. 46. We are working with the 2 digits. Okay. 42 plus 3.3 is 45. 42, aha, 42 plus 3.5 is in default rounding.
46.
46, has to be even. Then what I wrote there, 43 plus 3.5 is 46. We are on the other side of the ULP, right? Right. Haha. 42 plus 3.3 minus, plus, so which is like that, 45. Now remember, the order is respected, so it's like this, is, it's obvious. Now you 42. No, we are, no, sorry, I just went down here, sorry. Okay, 42, follow 42. I jumped one line. Okay. So we are okay. So we go back to the previous line. So 42 plus 3.3 plus 3.4. Remember that the parenthesis around this is 45 plus 3, 48. 3.4 plus 3.3 plus 42. 49.
I'm confused by the 46. Sorry, yes. 43 plus 3.5.
Yes.
The other one,
the one below.
the one below.
That
This is
one.
47.
That's 47.
No, it's tied to even.
How do we get the answer for 45 then in the one above?
The one above.
Yes, because it's always so. The correct result of 42, this is fundamental. 42 plus 3.3 is 45 point. So 42 plus 3.5 is 45.5. Okay? So this is middle point. Middle point. So middle point tie to even. So it's 46. 43 plus 3.5 is 46.5. Middle point. Tie to even. 46. Okay? So this is 45. This is 46. No, this is 44. This is 46. Once, so we always, okay, we'll see. 47. We always go, if it's in the middle point, we always go here. We never go to here. Okay? Tie to even. Okay? Tie to even. Yes. Okay, bye. Okay, so 42 plus 3.3 plus 3.4 is 45 plus 3, 48. Huh? 45 plus 3, 48. And 3 plus 3.4 plus 3.3 is 6. It's always 48. Why I said that? Yeah, most probably the example should have been different. Should have been 3.4 plus. Ah, no, 3.4. No, 40.
That's 3.7.
49. Yeah,
Yes.
which goes to 4. Okay.
Yes.
Yeah. Okay. So yes, I will redo. So we'll redo this. 40. You understand that if we were doing in binary, we were still to the first one? Okay. Okay, so 42. No, 42 plus 3.3 is 45. 45 plus 3.4 is 48. 3.4 plus 3.3 is 6. 6 plus 42 is, no, is 7. It's equal to 3.7 and then it's 7. It's clear this one to everybody? 3.4 plus 3.3 is 7.0. No, it's it's 7 point. Why you say 3.4 plus 3.3 is not 7? It's 6.7. 6.7. It's 3.4 plus 3.3. This is exact. Is 6.7. It's 2 digits. 6.7 plus 42 is 48 plus 7, which rounds to.
It's the wrong symbol for that, no? Sorry.
Yeah, no, this is correct.
The symbol is the.
No, 3.4 plus 3.3, there are two digits, is 6.7.
Yes.
It's in 2 digits.
Yes, understood.
So I have a question about, so when we sum up multiple ones,
Yeah.
do we first always have an intermediate result that is already rounded? Or
Yes.
do we round the final result?
No, otherwise that would be a special function which doesn't exist, but you can write, we can learn how to write. That would be a fused triple sum, which is the most wanted operation from the hardware, which hardware people don't provide. Okay? So you will first do the first two, it will round, and then it will sum.
So it means that the order can change the result. So actually the equal sign is wrong on the slide.
No, it's not wrong. It's wrong if I would have written this symbol. But I have written that symbol, and that is correct.
But one result is 48, the other is 49.
Yes, that's what I wanted to prove you. Because that's the whole thing of this is the last line. Read the last line. Read loud the last line, please.
Floating point arithmetic is
not associative and can lead to loss of precision up to catastrophic cancellations.
Right?
X plus epsilon minus X is not equal to epsilon.
It can be even 0 or infinite. Okay, so that's the whole thing. Okay, so 6.7 plus 40 plus 42 is of course 40. 49, yes, 49 is 48 plus 7, which okay. We can do it in decimal. I wrote it in decimal. Don't worry. We can do it in Python, and you will write all this. Okay, but I wanted to do on the blackboard. Okay, but if you click on the next on something, we will click it because this can be done in Godboard. Decimal works in Godboard. Is this clear? If it's not, we have to repeat everything from scratch because this is the after the ULP. That's the most important thing that we have to learn. Okay, which is this, which I have proved here. Okay.
Precision. So when we say here decimal precision 2, that means 2 digits.
Yes, as I told you, this will be confusing because in floating point arithmetics, the word number of significant bits or precision is used exchangeably. Although, as a scientist, we would prefer precision to be the precision. But the precision is relative. Okay, so we always say relative precision. I mean, what is the precision of what? Yeah, it's the ULP. So usually precision and number of significant, you see, precision 2 is easy. Number of significant bits is 2. In addition, there is the problem between number of significant bits and the length of the significant, which in binary is different, is 23, 24. Okay, so I told you from beginning that I'm very sorry, but precision and number of significant digits will be confusing. Okay, so we say precision 24, which is single precision. Okay, so of course it would be interesting to know that I did this with this funny decimal precision 2 number, just because I think that we managed to do the example, and this now it should be more or less in your mind easier if we would have done all this using bits. I hope disagree. Because then when you do the math, it will be, okay, good. Now, we said cancellation. So let me introduce this as the example. So this is the most classical example of cancellation. Okay? So at middle school, no, not probably middle school, but college or whatever, before, it's surely undergraduate, no, less than undergraduate, high school, you have learned that the solution of the quadratic equation is the one I wrote there. This is, of course, copied from Wikipedia. So. And there, as you notice, there are two sources of cancellation. Because there are two subtractions. One is inside the square root, which is the under 2 is the determinant, usually called b squared minus 4ac. The real risk there is that it becomes negative. If b squared is very close to 4ac, you can get a negative number. But it does not really affect much usually computation. The one which is nasty, and is can easily go nasty, is this other one. Because if 4ac is small with respect to b squared, and becoming small is easy, because as soon as you square a number, you get big very fast, this becomes b minus b, and is 0. While the result could be a number which, of course, is much smaller than b, but is big by itself. I mean, we have seen it here, right? We have not done the last bit. This one, right? 42 plus 3.3 minus 45, that's 0. right? But 45 minus 42 minus 3.3 is 0.3. 0.3 is, yes, you say, oh, but it's small with respect to 45. Yes, it's small with respect to 45, but in itself it's big. It's 0.3. It's not 3 10 to the minus 15, right? So here you get it. Now, of course, this is rather trivial to solve if you remember that a square minus b square is equal. Correct. So you take and you multiply the two solutions one for the other. You divide the denominator by the other, and you get this, which have even a name. There's even a guy which did this, what you did in 10 seconds. Excellent. You can name it. So this is, so you can rewrite the two solutions in this way, and the cancellation is gone. Okay? So this is a very trivial, not trivial, very clever, very clever transformation, which will make an equation which has a very nasty cancellation in something which has only one of the two cancellation. But as I said, the b square minus 4ac, just make sure that it's not negative. Many people just say ABS. Most of the computation will continue to. The other one, no. I mean, you get wrong number fast. Okay, so at 10:30. Oh, I know everybody's. We are a bit. The point is that if we don't go this, yeah, we don't have much. But I mean, we have done already done something very. I mean, that would need. I think let's break. So let's do like this, because we have till 12:30 or what? Or till 12:30. So we do like this. Because my idea was to finish, then start, and then you had all the time to do the, during the break and doing the exercise, and we discuss the first part. On the other end, I'm a little bit, I mean, I feel doing all this really tired. Now starting on something which is of the same level, maybe starting. So depending on you, I can go for another 12 minutes, and then we do the standard break, or we break now, and we restart instead in half an hour. As you like. Or it's okay for you, maybe we break, you rethink of everything I said, okay? And then we continue a little bit with this, and then we get the exercise. Okay, I think this is should be 15 minutes, but should be okay. All right. Also, okay. Also, because it starts to warm up, huh?
Can I make two questions?
Sure. No, we are in the break. The break, you can do whatever you like, and I'm always here. Yes.
So the difference between infinite and
Please.
the difference between infinite and none is just a single bit.
It's in theory not. It's the whole significant.
Okay.
So if you are on the mailing list, so that's the payload of the none. So the significant can be used as a payload of the none. In fact, there is quiet none, signaling none, but in principle, you can write there a code to say, oh, this was from 0 over 0 on the square root, okay? So, but it's never been used. And no one is using because they have this stupid exception, but the exception are stupid, okay? So you could use the significant because it will be propagated, although the problem is that so none propagates. But if you have two nones coming from a different source, how it should propagate? Or if then you have a none and then you start to make operations, which operations, you know? So they are discussing, but if you want, you just say the payload of the NAN, and you may find a wonderful discussion about how to standardize the payload of the NAN.
And the second one is here, the floating points, they have the same distance between the previous one and the next one?
Up to the, between 2 binaries.
Yes.
Like 2 or 4, 2 or 4 will not be the same.
Is there any number representation where the distance is not equal to the previous one?
No, I don't, it's not a floating point. It's not of the type m times x to the n.
Yeah, but is there other type of number?
Let's think about. I don't think so. I mean, you have to distinguish between the floating point and its binary representation. Okay, so, but in general, even so, there are two cases. Is given the floating point as an integer, if I subtract or subtract 1, is this before and next? Not necessarily, although it's true for all. Because, but if you write it as an arithmetic quantity, so m times 2 to the n, I don't think so. You can ask, but it's not a floating point. It's a whatever. Because you can have representation in which the mantissa and the significant varies. They are infinite types, and the decimal as a packed representation. Because if you represent a decimal, then you waste, either you use 3-bit, 4-bit, and then you waste, because 9, and or you use a packed one, so that you do up to 8, and then 9 you represent somewhere else. But at that point, I suspect that if you do +1, -1 in binary, in integer, it will not go to the next after, next before. Oh, no, I was, in fact, as you know, they even touch decimal. Because otherwise, also because unless you are not really working with decimal, and then you will study, but while binary, no, you have it there, bang. Okay.
What does that mean? So that we can. What do you think of it's called the POSIT?
Yeah, the POSIT. So there was a long, there was a long story of the POSIT. The problem of the POSIT is it's not really efficient, despite of what he's saying, and it's difficult to represent. And so there was a paper, if you see some friends, which implemented even in FPGA and said, come on. Yeah, and then at the end it doesn't give much with respect to the, so the POSIT could be one of this number that, but no.
No, but I heard it was like floating.
Yeah, with the precision which, with the precision which, I mean, he has his interest, but at the end, people haven't found real way. It's surely very difficult that it could be implemented in hardware, and getting efficient in terms of computation, at the end, you don't gain much. That's what I understood. And so besides the father to be himself, which went then, this was a strange story. It was at IBM, and then he went to NVIDIA, something like that. He did something strange. He was suddenly, he moved. But then I think he was trying to convince people to use POSIX in hardware. And most probably thought that there could be an opening, instead of all this. But now, now they are talking about floating point with 3-bit significance. There is the standard, it's the new standard of floating point for AI, which even defines 3 bits integer. Oh, ma dovete provare l'acqua, cioè io penso, lo so, infatti me la sono presa, però.
Exactly. Whenever it's good, and I'm going to write ingredients. But you never know. They're I saw this morning on breakfast.
Decimal digits means that if you print it in decimal, like 3.1415, whatever, how many decimal digits it corresponds. Okay, so if you don't write in binary, right? You use in decimal. So in how many decimal bits? Of course, it's not exact, but it's more or less how many decimals. That's the number of decimal. So you write it in exponential form, right? So if you want to write it, that's why you see in having six, if you print it with 6 digits is not enough because it's 7. So actually you have to print it in 8 to be sure. So this tells you how many decimal digits you have to print in order to make sense. And if you write it more, they don't make sense, the other one. Okay? It's, as I said, the same is, what's the precision of a floating point number? 10 to the minus 7, okay? Actually, it's 10 to the minus 7.2, okay? So that's the exponent of 10 of 2 to the 23. If you want, if you have, was one of the exercises, if you have 2 to the minus 23 and you print it in decimal, it will be 10 to the minus 7. Yes. Okay.
Exponents can't be 0.
The exponent can be 0 because it's 1. Yeah, 2 to the 0 is 1. So, but the exponent or the bias exponent?
The exponent before bias, it can't be.
No, it's a 0 means that it's a 0.
Yes.
So it's a 0 means 0. So if you look, so if the exponent is 0, if everything else is 0, means 0. If instead the other number are non-zero, this means it's subnormal, means that the one in front is not. So it's 0 point something per 2 times to the 127. Then you can normalize it and it becomes to the 28, 29, minus 127, minus 128, 29, 30, depending how many leading zero the significant is. Huh? And you keep losing precision.
I'm finding a suit. We've got to try out. She's very good. Oh, it's too much. It's like we finish our life right side.
Decimal. Sì, ma non, però non supportano un pi, maledetto.
Sai che in Blue stanno aggiungo la libreria per fare
Decimal, sì, però tu capisci scriverlo così.
No, certo. Non so se è già finita dentro.
Ma è decimal standard o decimal? Perché questo è decimal la qualunque, capito?
No, quello è decimal,
Quello standard con la rappresentazione standard tremenda che per giunta può essere uno o l'altro. Le provate, le guardate la risposta.
No.
È il gioco delle dita.
Non ci provo neanche, però no.
Ma perché è carino, è il gioco delle dita. Tu scrivi questo, ma qua fino a 9, e 9 come lo scrivi? E metti il bit qua.
No, so che hanno
quindi tu scrivi tutti i numeri da 08, 08, 08, 08 e il 9 dove dei buchi, no?
No, hanno fatto due review, credo, la prima e non è passato e poi l'hanno rifatta. Non so se è già finita in una release, perché è una cosa abbastanza recente, sì, quindi magari in compiler Explorer sanno l'ultima versione di Boost, è possibile che ci sia anche il decimal dentro.
No, ma io per fare delle cose così Python stamattina dovevo calcolare pi meno e una riga di Python e l'ho calcolato perché
Ascolta, io purtroppo devo andare.
Va bene, no, ma io non mi aspettavo nemmeno che tu stessi qua.
No, ma io volevo anche dare una mano per gli esercizi, solo che...
Qua siamo chiusi. Vabbè, quindi no, perché lo devo dire. Non stiamo, perché se lo anche se non stiamo sul pulmino dello strega.
Devo prendere un po' di caffè.
Sì. No, vabbè, io poi non sono venuto perché volevo fare un po' di cool down, perché se mi mettevo poi su quelle è bravo, sì, è competente, è competente, il problema è se è bravo,
non ha molta esperienza di insegnamento, quindi
cioè che non si può aspettare,
no, però anche ha un modo di fare molto gentile, carino.
Sì, no, infatti mi hanno detto che
è da coltivare anche per loro.
va bene, sì. No, allora, la sua origine purtroppo è biassata, il poveretto, perché lui lui aveva fatto la tesi PC con sì, e soprattutto legato a René, ai tempi con GSI e a Carminati, GSI, e sul maledetto l'ARP. Quindi, capito, lui ha lavorato su un oggetto che non è mai esistito. Poi per fortuna è arrivato a VX 513, ma non era l'ARP.
Adesso portano avanti per 10 anni questa roba.
Appunto, che io sono d'accordo. Il poveretto, lui aveva anche fatto una cosa che faceva senso, dopodiché quelli ovviamente gliel'hanno cambiato.
È così che sia ritardata, però è stato tenace per più di 10
Cioè ho capito il fatto che non vogliono supportare A minore di B, perché devi fare select, ma se funziona, perché io non lo so nemmeno. L'ha fatto vedere. Cioè, se usi extended vector, se usi broken extended vector, tu scrivi A minore di B, punto interrogativo, A, B, e lo fa.
Ah, sì, infatti parlava del fare l'overload dell'operatore, le domande del punto, ma ha detto che vabbè, ancora non c'è, ma ci sta.
No, ma o c'è lo standard o non c'è, capito?
No, non c'è.
Ma il problema è sì, fare l'overload, capito? Perché no? Extended c'è. Però adesso che c'è il sim, se io l'avessi dovuto fare, ti ricordi, facevo questa cosa qua, ma e che faccio adesso? Gli faccio vedere extended, che è banale, il blend, poi lo chiamano, devo sempre chiamare, la istruzione l'abbiamo chiamata blend, ok, fa schifo chiamarla blend, ma Intel l'ha chiamata blend, e ora la dobbiamo chiamare invece select. Poi funziona, non funziona, come
quando
cazzo.
ci metteremo dentro SQL ascolta, io devo fare
sì, mentre che vai fuori richiama la gente. Ah?
Ma sei in pensione adesso?
Certo, da più anni.
Ma è cambiato qualcosa nella tua vita?
Che se non vengo non me ne fotte doppio, perché già prima non me ne fotteva più nulla, perché io a 2 anni ho dato tutto in mano e ho detto io non voglio essere responsabile di niente, cioè non è che io mi metto voglio fare quello che mi viene, dopodiché se mi viene bene, e soprattutto non voglio rispondere alle code review di questi coglioncelli, come dire, cambia la. Si è chiuso un attimo qua, non stiamo.
Sei andato appena prima della Yaslo, che secondo me è andata bene, perché adesso
But
You will find out in 30 seconds.
no, you know, maybe. Because to do correctly, you should do the sum also of A, comma, error with the other also with the error. And that's required. So the correct two sum requires 6 sums, or requires each time to come, because you remember this, the lemma says that only if the A is less than B by absolute value. And usually that is not done. Okay. Now the point is that in order to compute, as you have learned yesterday, if you want to do ABS of A is less than ABS of B, swap A and B, that's cost. And it's almost the same cost, you know, that doing 3 times the sums properly done. If you want to know, but as I said, it's too tricky. But in principle, if you want to do correctly, you had to do this. By the way, in AVX 512, they introduced an instruction, very complex instruction, which is able to do min and max for if the ABS. So it does. But that's an instruction. Oh, yeah, okay. And that's important in order to do, but okay, but that's really high level. So next module is about elementary functions, which is everything which is not plus n product, which is not an addition. So everything which is not an addition of a product, an addition is also the difference because it's already, is an elementary function, including therefore the division, the square root. The division is implemented. We don't want to enter the 10 different ways that you implement the division, including the one you have learned at elementary school. They teach how to make a division at elementary school. Okay. Yeah, I mean, there are an algorithm which I think there is a name for that algorithm, and they seem the implementation. So, IEEE 754, also the C standard, define a set of additional operations. This is the title of the, which of course we usually call elementary functions, which are the exponent, log, and power of various forms. We'll see it. Then the trigonometric and hyperbolic functions and their inverse, which usually we call the arc, right? The arc sine, the arc cosine. And in addition, C and C++ they define even more functions. You can have it, like the error function, the Bessel function of order 1. And the other function which may be more useful, or if I was asked by Jean-Michel Muller to count all this in standard code, how many of these functions I used. So I scan most of scientific code. You can find, for example, there is the phonics, the benchmark and things. Okay, the only one used are the trigonometric and the exponents. I mean, never see, which is a pity. Why don't use the error function from the standard library? Nobody does. Why? Because everybody has his own code. But anyhow, fine, they are also there, and you are welcome to use them. Because as anything else, each vendor or compiler provides its own implementation, and they all differ. So if you want, you can have, there is a compilation of the accuracy of, for various vendors which are used, common use, some other which are less commonly used in this paper, which today is Gladman et al. Those should be called Paul Zimmerman et al. which is the most accurate implementation to date, we believe to be the one from the core math project led by Paul Zimmerman, which you find in this link, and that's open source. It is open source, is considered to be a reference or implementation, so not necessarily implemented even for the architecture which is tested. So if you say, but it can be done, yes, do it. But, and then proof. Okay. No, I have not, okay. Fine. Okay, yes, maybe I have to re-implement my trick. No, what I did. Okay, while I'm finding my trick. So, so this is a list, a very partial list from the paper above of the various library functions, which various set of precision that we have found doing with a scan. As I said, for single precision is not a problem. You just do a scan of all possible floating point number, including infinite non-subnormals. And that's it. Here we don't have a counter. And therefore, as you and the function is correctly rounded only if the error is less than equal to 0.5. Huh? Remember, the error is 0.5. If this, so this is in ULP. Huh? It's a relative error. So that's the error, the largest error found doing a scan on this function on all possible floating point number, including in double precision. Is tricky, but it's not guaranteed, but it's at least larger than that and is correctly rounded only if it's 0.5, which is okay. So you notice these are the GNU library. This is the Intel, AMD, Nulib, Muse, Apple, LLVM, which at that time was mostly not implemented, CUDA, and ROCm, or if you prefer, is the AMD library. Okay, so this is, so as you notice, most of the library do not reach the correctly rounded, and in some cases are very quite far away, completely wrong. This most probably is not true. Is to be some. You can get a large number for the if a subnormal number is giving 0 instead than 10 to the minus 25th. I mean, okay, so this could easily be 2 to the 23, which means that instead of 0 gives the smallest value, instead of the smallest value is 0. Okay, this is the problem of ULP. It's not the absolute value, is in ULP. So for instance, the Apple for ACOS should be a very large number because we know that it returns the 0.4 instead of doesn't return the correct number, the correctly rounded number otherwise. Okay? So this is to give you a little bit the fact that it's implemented is essentially depends on the implementation, and sometimes you don't even reach the faithfully rounded, because if it's larger than 1, it's not even faithfully rounded. It's more than 1 ULP, the maximal error. Now you have to be careful because we are nasty. We are scanning all possible floating points. Okay? So it's not, so here we are really looking to the sign of 10 to the 52. Now, who computes the sign of 10 to the 52? Yes, but it's something you can type and ask for a result, and the result is a number. Yes?
Then, okay, I'm not sure I I am understanding the, let's say,
The impact.
how to use this table in the sense of, would that mean that I have to prepare some library, in the implementation from some library with respect to the others? So for example, if I look at CUDA,
Yeah.
it seems quite large with respect to IML, no?
Yeah, the difference is that AML is proprietary and is available only if you buy the on x84 on Intel machine, maybe on AMD, and the result is different. I will not. Well, we could discuss that. CUDA is CUDA, yes, but this is it, which means, and this again back to the infamous problem of reproducibility, that if you run a program on your laptop and you are running on Apple or you are using GNU libc and then you do it on CUDA and the number is different. And if you have a cut on a random number in Giant to decide if you go on the left or on the right, on one machine will go on the left, the other machine goes on the right, and it completely differs. And your result, so don't expect reproducibility as soon as you use a function, unless you are not using a correctly rounded implementation. So the message is this.
Okay, but then isn't this a problem for pushing?
Could be a problem if you depend on this level. It's surely a problem if you want bitwise reproducibility. At which level depends, but it's a problem, and in fact we see it, and that's why many people say that the only solution is to have correctly rounded the result. The other possibility is that you code it by yourself, or you use an open source code, and instead of calling the function provided by the vendor, you call your own, and provided that the compiler, because we have seen that with FMA of CUDA and on IBM give you the same result, then maybe you can progress further. But
because then I was wondering when you make the error, if you usually do the also considering this, like you try your program in different libraries and then you do the difference in the results.
Depends on the accuracy, but we know that at trigger level, I have spent my last year of activity in chasing the why we were triggering or not on something and why was passing and not. And I was contacted by Paul because there is an infamous talk by somebody who said that essentially the precision was was making this the Atlas experiment not seeing the X, which is not really true, but it's true, and you can prove it just running the Atlas software that if you run it on AMD or Intel, it produces completely different simulated. But statistically, statistically they are equivalent. But there is a full paper, okay, there is a full discussion on this, particularly for climate people. If you want, I think the references, I have it, and it's very interesting topics, but it's not the topic of today because we don't even take time to arrive to the end. If we go, but I have a presentation on reproducibility if you want. You just look Vincenzo Innocente, reproducibility, and you will not get the answer, but all the anecdotes on the thing. Yeah. No, it's not. If you are interested in reproducibility, you tell the boss, and before I go to holidays, maybe we can discuss about reproducibility. So how you evaluate a function, sine of x? So essentially this is done in 5 steps. This is not, again, it's not computing. Again, the table. You know, in the 17th century, they were computing the table of sine of the functions, you know. So people were computing because they predicted, after all, the dynamics of Jupiter and the satellite with high precision. So they were able to compute functions with several digits. They were the table maker. So all this is things which are known 200 years. There's nothing. So the first things which is the first of the or the last, because again, think always parallel computer. None. I mean, yes. So there are special values, in particular underflow, overflow, invalid. Imagine the one which I hate most. You know, 8 and 2. 8 and 2. The arctangent of two numbers x, the xy. So the arctangent of x over y, y over x. If x and y is 0, okay, you would say it is not a number. No, it's 0. Don't worry, it's written in the standard. You have not to think. You read in the standard, for each function, there is a list like that of what is the result if the input is some bizarre thing, okay? And so you have to respect it. And there are also the special. So the first things you have to do is the range reduction, because usually functions are easy to compute in a small range and not over all possible floating point. We'll see. We will go in detail for each of these steps, but the first one, because once you have the function in a reasonable range, you do an approximation, right? Taylor. Everybody knows how to write the Taylor expansion of the exponent or sine, right? And you have done it at first year of undergraduate, I suppose. That's an approximation. It's not the best one. And then you get the number, which is an approximation. If required, and we go back to the previous point, most of the thing arrives here. And now comes, if it's required to have a precision better than what you get, which is not even, I tell you, faithfully rounded, is a couple of word people. You do a precision test, and then you have to handle the table maker dilemma, which will go on, as you've seen on Monday. Michel Muller will talk about 25 years of handling the table maker dilemma, which is a problem known since the 17th century. It's not something we have invented in the last 25 years. Okay. Once you got this, you have to go back to the full range. Okay? So, range reduction. So, let's do that. We have to do the log of a floating point number. That should be easy. I should not even tell you, right? A floating point number is 1 dot, the mantissa, the significant, 2 to the n. Where this means that if you take this number, the significant, this is a number between 1 and 2. It's between 1 and 2. We agree? Right. If it's larger than 2, 2 plus 1, and we continue. Right. So what is the logarithm of this number? Yes? Logarithm base 2 of this number. Say base 2 is easy. Is the logarithm of 1 plus dot m plus n. Now it happens that the polynomial expansion, not Taylor, but of the logarithm between 1 and 2 is complicated, because the logarithm is one of the worst functions to do Taylor expansion. In fact, you don't do it around 0. Of course, it's not Taylor expansion. It's around 1. But even around 1, arriving between 1 and 2, it's far. So what you do is actually between 0.75 and 1.5. Okay, so you have to take a number between 1 and 2, and you have to make it between 0.75 and 1.1, keeping the exponent integer. You don't multiply by 0.75. Okay? I leave the solution to the attentive reader that we discuss later. Okay? They think how you would do it. Okay, you have this number and you want to do it, you have to do it in this form, where y is between 0.75 and 1.5, z is integer, so that you can then do that. Now you say, but z cannot also be non-integer. Yeah, try to compute it. Do it, fine, do it. So when you have this is easy. Log 2 is a constant, right? Yeah. And log y, we compute it using a polynomial approximation. Next slide, okay? For the exponent, it's a little bit more tricky, but not much. It's nothing to do with this, it's the reverse. So we want to arrive to a form like this. Okay, so we start with x, and we write x as usual as k star log 2 plus y, where y is a number between minus log 2 half and log 2 half. It's a tricky reason why divided by 2. Sometimes people say just because otherwise essentially 2 to the k will overflow. But anyhow, again, how you k of course has to be integer because you want to write 2 to the k, and then x of y in this interval, again, if it's not the Taylor expansion, is whatever. This is really x, it's not 2 to the y, it's x to y, one computes it. How you go from this number, which actually doesn't matter, forget about this, it's x. How you go to x to this, it's easy, if you think. You have actually to have y in this one, but again, it should be easy. Think about it. This is just floating point computation. There is no magic. You have not to do any magic. It's just trivial. So that then once you have it, it's obvious. You do 2 to the k. And you get also the x because of the magic of not. But the power, if the y is not, so if y is an integer of the inverse of an integer, then there are other technique. Otherwise, you should just write ey to the log x. This now comes the fun. In the new standard, there are 2 power. There's one power, which was the old po, and then there is the new power, which is called po-r, which says, no, it's the result of this. Because, again, is the problem of infinites, or so that if you ask x to the y correctly rounded and valid the whole possible interval, it's much more complicated than just say this has to be for all possible value of x and y. So because otherwise, you get a huge amount of special cases that you have to deal with the subnormals, and I mean, this overflow fast, really fast. I mean, after all, in single precision, 2 to the minus 2 to the under 29 is overflow, it's infinite. The largest x of an exponent is small, it's in the order of 15 integer. So this you have to deal with. And if you want it correctly rounded, it's tricky. So sine, cosine, tangent, and atan 2, right? So what's the sine of 2,554? Come on, nobody wants to. Yes, we have to produce also this number. Okay, so of course, Now, can you imagine it's here, you see, here they are also written. So you have to imagine the circle, right? You remember the trig identities, right? Everybody knows the cosine of pi minus x is equal to the sine of x, so on and so forth. The cosine of pi half minus x is equal to the sine of x. So anyhow, if you imagine all this, you can just compute sine, cosine, tangent, and all between 0 and pi half, pi quarter, so the first octant, okay? So you reduce everything to the first octant. Now you can also do minus pi over. The sine is odd, the cosine is even, right around 0. It's okay? Right. So, or you compute between 0 and pi 4, or between minus pi 4 and pi 4, usually the Taylor expansion or the whatever will work. If it's the same number, it's just changing the sign. Okay, this is why I say if you said you do this is of course with the standard rounding. If you do the bizarre rounding, you understand that you break already that sine of minus x is not equal anymore to plus. That's okay. So the point is that it's not trivial, because it's trivial for f2 pi x, which is called sin pi, which is quite easy because this is a fraction of pi. Okay, so you just take the integer away, twice the integer, and then you immediately arrive here. Okay, so if you have a number which is 9.7 pi, you subtract. You have to subtract 18, but if you subtract 9, you already, you are inside between 0 and pi. Exact. It's an integer operation. You have not done anything special. If instead is in radiant, it's a pain because it has to be correctly rounded, this game. And this is non-trivial. And even if you read it, I mean, if you have it like this, you read the 9, immediately you know where you are. I mean, it's odd. It's like pi to pi, you know where you are. You multiply by 2, tack, you go back to the octet. But so you get this, you compute it, and then you use what you have found, how many rounds you have done in order to go back. So if the number was between pi 4 and pi half, you have to take the cosine if you were computing the sine, and the sine if you were computing the cosine. And then if you were on the other side, you had to take the minus sign and so on and so forth, which always make me mad anyhow. And again, it's something that with a bit, I think, this one, it's easy. I mean, come on, in 10 minutes you have to get this right. Okay, this is the exercise, fine. If you can get it in 4 hours before you get it correct, I mean, this is, and optimized. Yeah. Yeah, I mean, yeah. So for what concerns asine, acosine, and hyperbolic, that's more tricky because they have a tendency to have, how we say, tangent, I mean, the asymptotes, okay? They are so they have asymptotic behavior. And if you have a function with asymptotic behavior, a polynomial doesn't work well in the asymptote. So usually you divide in various pieces where it behaves nicely. If you think of ACOS in particular, like that, because the region between 0 and 0.6, 0.7 is really nice almost parabolic. Then it just, of course, again, you can use the trig identities between asine and cosine, and you switch back. But it's back because it's x squared minus 1. You have to do that. Okay, so usually you approximate in ad hoc interval. Of course, when you do this trick, you have to make sure that it's continuous at the edge, which is not trivial, it's always a pain. Okay, so the approximation. Now, if you have to approximate a function, you don't think. You go and look in the Abramovitz and Stegan, which is the reference since 1964. They even now, in what they call a digital library, if you manage to have correct display, tell me. If you click on this, I cannot read it. Sincerely, I cannot read it. The Abramovitz and Stegan can be found in its original form in PDF in almost everywhere. It's even in Google Books, so no problem. If you don't find what you are looking in the Abramovitz and Stegan, look back. Okay? It's impossible. All right. Now, in general, of course, so the Abramovitz-Stegan will give you also this, also some very compact form, but don't expect most of them. They are really an approximation, often surely not correctly rounded, huh? But they are good enough for many things that you do. If you, in general, in code, what is used is this is called this is fun. Shift and add algorithm, which is interesting because was used in you don't need multiplication, and why Cordico? Yes, because was implemented in x87, which is is still emulated. Is the floating point accelerator or unit of the Pentium, essentially, of any other of the Pentium, actually. That's why it's A7. And of course, in the lunar orbiter module, in the Apollo guidance system. And everything which is implemented in the Apollo guidance system requires to be quoted, right? Like the Kalman filter. I don't know if they will talk about Cordic in doing FPGA. I don't think so, but okay. Anyhow, shift and add algorithm. Of course, you will find mostly polynomial, but polynomial, usually they don't use Taylor because Taylor bad behaves. I mean, so usually these are used using orthogonal polynomials like Chebyshev or Legendre or whatever you like, which usually the Chebyshev using a norm which is called the superior, which means that it's the maximum in the interval. Okay, so you can have a Chebyshev set, and then you compute the coefficient of the Chebyshev in such that the maximum difference with respect to the expected value is less than something. And this is what you want, because you say should be the relative error should be less than 10 to the minus 2 to the 23. And so is correctly rounded, which will never be, but okay. So this is the standard. But with the problem is that while with the Taylor, you can always go more and more and more, add more, still the two numbers will be equal, and that's something we have the example here because it's trivial to do it. With Chebyshev, of course not. You don't because you resum all the polynomials and you re-put it back into a polynomial form. It's not that. So the implementation will never be Chebyshev 0, 1, 2, 3, 4 with the coefficient, because then you have to do many more FMA than what required. So usually the result is a polynomial order 5 or the 7, whatever. It's not the 5 polynomial. So, okay, but okay, you can always do this. This is in order to do the precision test. With the Taylor is easy. You continue to expand till the result is identical. You add a new tile, the result is identical. The other approximation, which is very nice, but people don't like it because of a division, and as I told you, machine dislike precision. Also because the division is not an operation we have not introduced yet. So how you can use a rational polynomial if we don't know yet how to do divisions? And so they don't like it. Particularly Intel people don't like it. But there are many other people which likes, and this the so-called Padé approximation, which in particular is very nice, is very useful for this asymptotic behavior. So if you have a sigmoid, you know, the sigmoid is everywhere because of the old machine learning. Okay, now they're gone. I mean, it was too slow, but you still find this the arc tangent, the F function, you know, all these sigmoids. Polynomials, you will never get a polynomial. There's no way. You can have the polynomial in the central part, and then the asymptotic, you have to go back to Abramovitz and Segun and write down the asymptotic part. And then at -8, you have to say, well, okay. The other one, which is of course also very nice, of course, are iterative methods. When, if you know, like a fixed point theorem, if you know an approximation, then there are ways iteratively to get the correct results. For instance, using Newton-Raphson. And if you want to know everything, there's this wonderful piece of paper, which of course is approx functions, which will tell you everything by the professional. So what about square root and division? So usually the division, you can implement it as a product between the numerator and the inverse of the denominator. This is one way, but there are many other ways. Okay. So for any power and inverse power of a real number, you can use Newton-Raphson approximation, starting with an approximation of the significand. The exponent is trivial. If you have 2 to the n and you have to do the square root, if n, the square root of the 2 to the n is 2 to the n half, right? So if n is even, is 2 to the n half. If it's odd, it's still 2 to the n half, and then you put the 1 to the, you push the 1 to the mantissa, and you go on. Okay? So you need to have this approximation. And now comes the magic, which is again not true. This was known well below. As usual, there is of course a unpublished paper and by Kahn, which described this. Of course, Kahn knew it. So this is the called magic fast 1 over square root that is in Quake 3. Why? Because if you are a game, the only things that you do is to compute the distance between 2 points. And in order to compute the distance between 2 points, you have to take the inverse of a square root, right? You normalize. And so gaming was really limited by 1 over square root because they don't do matrix manipulation, they do geometry. And so they invented this fast, which is this trick. Again, if you want to know everything, you can read there, or in the previous paper by Jean-Michel will give you full details about this, which is, this is the famous union, which will, so this is, here there is still the old style, because this is almost the original code from Quake. Okay, so this is the old way of doing it. Now is undefined behavior. So this is the magic which will give you the approximation. And so essentially here you see, here it essentially takes the number is positive, of course. Also if it's negative, it doesn't matter because this one will remove. But you shift, so you divide by 2 the exponent. And if it's odd, it will move to the mantissa part. You see? You take the floating point, you shift. So if it's even, that's no problem. The yes divided by 2. And And of course, then you have the magic subtract 2.7. Okay. So this is a magic number, but can be justified. I will not justify this fully. If you want to know all the details, it's written. And this is the Newton-Raphson that you find also in the funny thing is that this will produce a number which is always smaller than the real square root. So in reality, you can twinkle these two numbers so that it goes a little bit higher. And also this number you can, there is full papers about how to slightly re-optimize this magic. Of course, everybody knows, and so you will see, as I showed you, that they have implemented this and the equivalent of it for the 1 over x in hardware by this function, rs squared t and RCP, which you find it in, which you can access, as you learned, using intrinsic. And so this is real code which will do this in x86-64. This is for 1 over x. And this is not correctly rounded. I think the exercise is to try to make it correctly rounded. I think it's not even faithful, but okay. And in particular, the 1 over the square root of 0.1 is particularly nasty. Yeah, never use 0.1. Okay, rule number 1, never use 0.1. I mean, there's no reason to have a constant called 0.1. Just use a power of 2, please. If you have to have a constant in your code, make sure that it is properly representable in floating point. And never, ever, ever use 0.1, 0.3, but in particular 0.1. 0.1 is nasty. You don't want it. It's guaranteed trouble of precision. You have seen it. It goes off immediately. And 0.1 is hard to round case of square root. Okay? You just I have a perfect square root. Try with the 0.1. If it works with 0.1, it's true. If it's not, I did it. And of course, failed the test of 0.1. So what does it mean, failing the test? That's table maker dilemma, 25 years on Monday. So what is the table maker dilemma? So again, well, you find at least 5 papers on this subject. So these are our floating point numbers. And these are the middle point, the half tick, the one which are not there. Okay, this one. Good. Now we compute a function. And the result is y. With an error, we can compute the error. You know how to compute the error, you do the derivatives, standard thing, okay? If you have sine of x and you do a polynomial, you can compute the error using the well-known ways. I mean, you know, the error of sine x is cosine x, right? The derivative of sine x is cosine x dx, huh? Yeah, good. So you can compute the error on sine x, no problem. Now, so you have a value, and you can compute the error. Now, you want to have it correctly rounded. So if it's here, remember, this is 1, you remember pi, right? Pi was there. So if this is the midpoint, so if it's here, or even if it's around there, and we are round to nearest, okay? Round to nearest, this is valid for any rounding. So round to nearest, if it's there or there, where it will round? Where it will round? It will round this, right? If it's round to lower, towards 0, say this is positive, we will round there. There's no problem. Okay. Now let's assume that instead it's here. Okay, so it's somewhere, but the error includes the middle point, or you are doing direct rounding and is around a real number, okay? Where you round? You don't know, I tell you, you don't know. Okay? Because there is the middle point. Forget about that if it's positive, no, that you don't know. It runs here or there. If it's here, it runs there. If it's there, it runs here. Okay? But if you compute and then the error overlap with the midpoint, which already tells you that in order to do correct rounding, you have to compute the function with at least one more bit. Augmented, that's why augmented sum, augmented multiplication is required here. You cannot. Okay, so you need a little bit more bit. Huh? And so when I go, and in general, so you don't know. And this happens, for instance, it's very simple to see. So in general, when this happens, is that there are two cases. Either is at 0 followed by all 1, or is a 1 followed by all zeros. What in digital is 7.45. Yeah. So we are in the middle point. Are we real in the middle point? Huh? So things now they say, well, they say it's trivial. I mean, it's easy to find because you can scan for it. Okay, because with the floating point, with single precision, you find it immediately. It's trivial. I mean, so for instance, if you take the sign of this number, now I think I did this 5 times. I think this one correctly rounding. Again, this is written in decimal. Okay, you have to write it in binary to get it correct. But okay, so you can do the sign of this number, which correctly rounded is a floating point. Is correct, and you get this. This is if you compute it in double precision. So this part is the one which should be your result, the red one, because in single precision, right? 1, 2, 3, and this 2. This is 2. Remember, so this is odd. And then there is a 0, the middle point, and then 1, 1, 1, 1. Till finally it's not 1. But you see how many and this is the other case. So this time, we are in the middle point, you see, because this is odd. You see how it's so useful, the non-number, okay? So this is actually is not 3, it's 2, but the result, if you add 1 bit, is in the middle point, it's 3. So we are in the middle point. And then you continue. And we continue to stay in the middle point till it becomes big. But you have to arrive here before you know that you have to go to the left or to the right. Of course, all this is irrelevant if you do faithful rounding. You don't care. Because faithful rounding means that if you are here, you can return or this or that, we are happy. And if you are here, you can return either this or that, and you are happy. And usually you return the even, right? Because this is midpoint. I don't care. Okay, but that's the main difference. That's why many people say. So the main difference, and this can take forever. So you can, if you want correctly rounded, it can be 10 times lower than faithful rounding. So this is called the table maker dilemma, because of course, in single precision, it's easy. In double precision, I mean, they say, I mean, fine, you will find examples where they go up to 128 digits and they even more than double precision, and they are still going, okay? So it's an interesting it's a problem. But if you want faithful rounding it doesn't exist. You have, it's just enough one bit, and then you know, and it's finished. And one bit, you have seen it. Yeah, you have to spend the time to do the a little bit of augmented sum, but okay. The problem is that there's no augmented FMA, and so it's costing. Yeah. So this is it for what concern what is around. But this is all science, as you see. Enough of the discussion about this about that. Okay, but it's fun, it's interesting. And now we conclude. Yeah, these are the exercise that we will see. Okay, 5 minutes, questions. We can do some interesting exercise that I will propose you later. This is fun and easy to do in Taylor expansion. Using Python. I think the code I propose is in Python. You can copy the Taylor expansion from Wikipedia, no problem. If you want, if you don't care, fine. Yeah. I suggest you not to expand the factorial. You just type it in. I mean, it doesn't matter. We are not for speed. Okay, so don't say, oh, what's the factorial of 12? You don't need to. You put together with the x. Think when you do the Taylor expansion, put the factorial to x so that you have only to multiply 11 times 12 for the previous one. It's x to the 5 over the factorial of 5 or whatever. In reality, it's x squared to the 5. Yeah. All right. And now comes, so the only part which at the end we could have done, because what we care is what we write. But if we do only that without knowing everything which came from before, we don't understand what it's all about. So we discussed about precision, accuracy, and speed. I could have had reproducibility, which is an issue as we have discussed, and comes together. And then you've seen tomorrow there is Christophe Gauthier, which says something which is fast and wrong. So we'll see. I will ask. I didn't want to ask him the slide before he makes the presentations because maybe he doesn't have it yet. But on Monday I will ask the slide. Okay. So what's the difference between precision and accuracy? What's the precision of this? So first of all, the precision of a measurement doesn't exist. The precision about the instrument. Okay, so this is almost undergraduate. I'm sure that even it's definitely undergraduate. Usually you do the first year, but I think that also in middle school they do it. So the accuracy of this object we have discussed is aesthetic. And if you are really crazy, you say that, oh, when you sum error, you use Gaussian approximation, so it's ethic divided square root of 12. Oh, great. So this is 1 millimeter over the square root of 12. Yes, I did it. I mean, everybody of us has done this. Okay, so what you do is that what's the length? This is really done. Kids of 14 years old, a technical student in Italy, they do this. So measure the length of your table using the quiz. Well, you do this, from this, up to there, each times the square root of 12 plus 1. Okay. At the end, we get a number, which is is 112.6 centimeter plus minus something. That something is the accuracy, it's not the precision. The precision remains the thick, so it's not, so it's usually that we do square root, that's not the precision, that's the accuracy. Okay? It's correct, right? I mean, if the kids of my friends are at the end able to do this when they are 14, I think that we got it. Okay, so that's the precision, and the other one is the accuracy. Good. Now, if your accuracy, required accuracy is 10 centimeter, why we have to use something which is precise at half a millimeter? Okay. So the precision, as I said, in our case is the numerical precision in bits, or if you wish, the relative error, whatever. We have already discussed the story of precision. That is 23, and usually comes from spec. I mean, a floating point has 23-bit precision, 10 to the minus 7 precision, not accuracy. The accuracy is the difference with respect to the truth. You agree? And it can be usually evaluated computing with a reference or a different algorithm, whatever you are used to do this when you look to this. To your measurement, typically we compare different experiments. That's why we have 4 experiments doing the same thing at LHC. And we don't discuss about systematic error here because that's not the topic. Then something important is the target accuracy, which is the acceptable tolerance with respect to the above. So again, if you are doing a measurement, but at the end your instrument has a precision of the 10 centimeter, there's no reason to do all the computation, in particular the representation using double precision number, unless you are not measuring the well, let's say centimeter into a phase space of 10 meters. If you are, of course, if you have a precision of a meter and you are doing astrophysics, well, then you need many, many bits. But okay. So the important point is to think in terms of the target accuracy and not necessarily use more precision than required if your target accuracy is large. And given the fact that most of our instruments are of the order of 12 bits, your preferred ADC, how many bits they have? 12? Yeah, so already 16 bits is not enough. So why to represent the energy of your calorimeter with a double precision, doing jet with the double precision number is, you tell me, given the fact that the precision of your calorimeter is 12 bits. Now, what about it after all? After all, doing in, so there's a very famous statement, you can hear still people that double are faster than float on Linux, which means nothing. But it was true in x86 because they used x87 to do all the floating point operations, we said, and the x87 was using long double. Okay, so since the advent of x86-64, all the floating point computation were done in long double, and long double convert in double without any cost. While if you go from float, it costs many cycles to convert from float to long double. So, and in addition, this long double has its own registry, which was the fun, particularly in Fortran, because depending on how the register, depending on when the long double was converted back to double, the results were different. This was typical before x86-64, because you compiled, then you add the comma, and the result was different. This was normal. So nobody cares about reproducibility because nothing. I mean, it was enough to change nothing. And because essentially it was keeping into this 80-bit registry as long as he liked. Of course, a compile time. Huh? And then it was going back to double when you needed to store it in the memory. But that was never clear, depending on the optimization. Okay. But this is not the case anymore, as you have learned yesterday, because also vectorization. So what's the cost? Oh, this you have seen it, right? He has discussed this. So this is, so you get it from Agner, all the table that, of course, you went through all the details, but I took it only from Ice Lake and Zen 5, and I forgot which page, because this is something like that. But so I just got, I think I got only the few pages which matters. For Ice Lake and Zen 5, which are the latest one. I mean, and this is the latency and the inverse throughput. Okay, you know, yes, I mean, yes. Thomas explained the difference. So this is what usually master. This is the inverse throughput. So that this number compiles. So this implies that he performs 2 add or subtraction for each cycle. Say how he can do it simply, he has 2 ports. So if the code is sequential, he will not do twice. But because he can do speculation, it can really go on. So if you have 2 instructions which are independent, he will do it in parallel, no problem. ILP, instruction ILP, instruction level parallelism. You have discussed yesterday. So this is the cost. In particular, you notice how the conversion to float to double actually costs more than a sum, typically, depending which one, which of the 2 machines. The commiss, so the comparison, is fast, but usually after a comparison, you have a jump or a mispredicted branch. And I think you discussed, he showed you with perf, what does it mean? Usually this is a phone call, what I call a phone call, because he has already done 20 instructions, and then he finds that it's false. He just throws away everything and restart from beginning. That's why we like non-branching code, right? You have seen it yesterday, non-branching code. So if there is no branching code, that's the real cost. If it's branching, this doesn't matter. Nothing matters because this is 100 cycles. Right. All these trivial instruction, really, they can even do full times. And as you see here, now the FMA would count. So this is in between, because also add and sum, all the rest doesn't matter. You do it with FMA, and he does 2 FMA per cycle, although the latency is 4. But the latency doesn't matter because this view is, he has not discussed architecture, because essentially they are pipelined. So if he can do one after the other, then he just continuously do it. And he can do this is up to 2 FMA per cycle. Okay? What about the division of a square root? Well, this is the real one and not the fast one. Well, the latency can be up to 20 cycles, which means, so this essentially can be up to 20 times lower. This is mostly on Intel because they don't vectorize. I mean, you have this big vector, but they don't vectorize the sum. They do it in 4x4. Okay, so that's why this number. On Zen is this. So just look to the small one. The big one is really because if you have this Z vectors, the AVX 512, the division is not done 16 by 16. Instead, the fast one without the Newton-Raphson is as fast as an FMA. But this one is 14 bits. Then you have to do the FMA, the couple of FMA. And then there is the move. I think he has taken you, what, for half an hour on the move, which is, of course, a copy. It can be as fast as nothing, but usually this means that it's operating between registry, there is no move, or whatever, I mean, forever, because if he has to copy it from memory, it can, I mean, depending where, it can be 350 cycles more. I think you had done measurement on these things yesterday? No. But so really, all this matter if you are not dominated by front-end latency or memory access, which is back-end, because usually the memory is coming from the back. But keep in mind this, because that's the typical speed. On the GPU is even different, because it depends which GPU you are using and what you are doing with GPU. GPUs typically comes in two fashions. There are GPUs for HPC, which costs a huge amount of money, and like the B200, and the one which we usually have, the gaming, or the one which is called for computing and for high energy, like the T4, and most they will use T4 most probably, L4, right? Which are not for HPC. What's the difference between the two? The main difference is here. Okay, so this is, well, this is the cost, if you wish, okay? Which first of all, you notice hasn't changed, but this is written 10 to the 2 for the L40, and here this is the H100, for instance. So the high level end still is more expensive in dollar than the one. But if you go to double precision, then is the opposite, okay? These guys, okay? This is why, because the high end do have 64-bit processor, which is only twice slower than the single precision, while the low end, like the L40 or the T4, they have only one processor each 32, so the double precision is 32 times slower than the single precision. Okay, so if you are using a low-end GPU, and the double precision will be 32 times lower than single precision if you are doing only floating point. Of course, if you are mostly doing memory access, you won't see it. And in fact, typically when they say, sorry, why your ratio is only 6? Because any real application will mostly shuffle data and not do computation. But we'll see. Say, okay, but what they do in reality, what they are doing with all this silicon in the last 10 years since the cost has not changed. I mean, where is the Moore's law? I mean, well, why? Well, because they are doing this stuff, this dumb stuff, this tensor core, which are used for AI, okay? Which even uses 16-bit thing. But the only things they know is to do matrix multiplication. So sorry, if you have to compute a polynomial, that's no good. But if you have to do matrix multiplication like GEM, then you can use augmented arithmetics using the augmented arithmetics of matrix, and you can use the tensor core at 16-bit to do computation at 32-bit or even 64. And they are even implemented now in GEM, And there is a famous Japanese professor which is now making his life on it. And if you go to the last NGT on floating point precision, you will see his talk and all this discussion of how you can do matrix multiplication using integer 8, literally integer 8, to emulate 64-bit gem multiplication. It's still faster because this monster costs nothing. Look this. So all the silicon is used to do this stuff. And that's why it's becoming impossible. Now, this is something I did on a T4. Okay? So I took a brute force inversion of a 5x5 matrix using Cholesky decomposition. It's a piece of code like that. It says there, okay, it's 32 plus 20 times minus and under 26 multiplication, so 5 division. Okay? So it's a little bit monster, which is just doing floating points, and you do it in a loop. And you see that once you fill up the GPU, so you fill up doing 512 of these big things in parallel, then the ratio is indeed about 32 between floating point and double. So if you do it in double, this is 32 times slower than in the float. This is the time. And I did it also what is called two-float, is augmented arithmetics, and that's what more or less you expect, 8 times slower. Okay? And the precision is essentially the same. So it matters. Okay? So this is what I want to tell you, that yes, we were used to use OX8464. Double is faster than float. But if you use vectorization, it's no more the case, but it's a factor 2. It's not easy to get this factor 2. Huh? On GPU, if you use the this type of GPU and you do intensive computation, which is not the case. I mean, here, come on, I'm not reading anything from memory, it's fake. But it's something that you can observe the factor 32. This is what I'm proud. I was managed to observe, because as I said, if you look, you will never get this 32 with this here. Okay, so what is our summary? In the old days, double was faster than float. On ARM, you can see a risk. Usually, no, scalar, float and double have the same speed. It's true. But the division squared and the memory bandwidth. If you have to read the vector of float 16, you go 4 times faster than if you read a vector of double. And so sometimes it's convenient to write in 16-bit if your accuracy allows, and then you move to 32-bit. That's we do it. We do it. If it's vectorized, SIMD, the float, of course, is twice faster than the double. Also because of this. On the GPU for HPC, float is twice faster than double, and the GPU, which are now sold as for AI, but they're actually the one that we use because cost less. They are optimized for low precision tensor operation, and if you do scalar code in float, usually you can reach as 32 times faster than float, than double. So having your code being correct in float is an advantage if you run it particularly on GPU or if you vectorize. Now, what about elementary function? This is again from, yes?
Explain again the thing about the bandwidth.
The bandwidth.
Yes,
I mean, you have to copy data from memory to the CPU. right? This is usually done in cache lines with, or not in pages. Okay, so they are in pages, then the page is indexed, and you have to copy it, and they are copied in cache lines, so 96 by 96. Okay, now, if you have a cache line, so it will contain 8 double precision numbers, 16 floating point, or 32 16-bit. So each time you read a number, you read in reality a cache line, and if you use it all, you get only 8. So with one read, you get 8 double, or 16, or 32 if they are float 16. So if you read the number from memory, the bandwidth to read the float 16, if you use it all, is 4 times higher than the bandwidth to read double precision. You will go faster, even if you are if you are prefetching everything. But if you are limited by memory bandwidth, which usually you are, then reading 16-bit number will be 4 times faster than reading double precision. And taking into account that convert it will cost you 3 cycles, most probably you gain. If representing the number in 16-bit is enough. And I guarantee you that unless you are doing very precise fitting, 16-bit is more than enough, whatever you are doing. I will not cover this. If you want, we can. But I thought that was too specialistic for high-energy physicists to discuss how to represent eta, phi, and pt in 16-bit. It's in the last 2 slides. So this is the speed of the real of function. In reciprocal throughput, if you go to the, you can also get the latency, which essentially for single precision and double precision. The scale is different. Now, you notice immediately that the bloody sine and cosine have a spike. This is because these bloody things that they have these special cases in order to be correctly rounded. But the exponent and they have fixed, so this is it. So usually this number is of the order of 10. Okay? Remember, the FMA is 0.5. So an exponent is 20 times slower than FMA. In double precision, is twice slower because you need, well, it's not twice, a little bit more, because you need more terms in the expansion. Usually it's not the case. They use a lookup table. So in double precision, what you do is that you do a couple of lookup. You divide the interval, for instance, between 0.75 and 5 in many more intervals, and then you have a first fast lookup table to go to the correct interval, or you do fast. Of course, there are functions which are crazy, but okay. So these are all the functions. These are all the functions that you can find implemented, right? But typically, for the one we use, or the log, okay, is about 10 cycle. It's not the latency. The latency is much slower. Okay, this is the inverse throughput. So these are done. These are inverse throughput. Yeah, it's not that it's not 10 per cycle. It's 10 cycle to do. But that's 10 cycle would be the latency. So it's 1/10 per cycle. Okay, anyhow, you need 10 cycle to do it. Okay. But as I said, do I need all this precision? Do I need really 23 bits of precision? Maybe not. And you can go faster. Okay? Because, of course, if you have the logarithm, in order to get 24-bit precision, you need an 8-degree polynomial. If you want 16-bit precision, you need the 5th degree polynomial. And if you have a 7-bit precision only, it's enough 2-degree polynomial. And here is a table by the done. This is done between 0 and 1 using Taylor. I don't even remember when I copied this, but I found it already done. But you notice that there is no chance arc sine and the square root don't work between 0 and 1 using Taylor. Okay. This I told you, there's no chance. Okay, but these are the typical precision. Of course, this is, you know, once you arrived here, you are already over. Okay, this is more than the precision of the single precision, right? But you see the log is always written as 1 plus x. We saw it because between 0 and 1, I mean. And you see, you need 8 in order to be over. In reality, if you do it between 0.75 and 1.5, you need only 7, I think, because you are very close. So if you only need 10 bits, then you can use, you know, very low polynomial. Say why? Well, have you ever think about, so if you are from high energy physics, you know these formulas which are copied from CMS code, but you find it everywhere. So the first one is the one which computes the multiple, both computes the multiple scattering in a medium. Then you go and ask your engineer, what's the usual precision in of the bulk material of a silicon detector? 300 micron. Well, 1%. And I don't say what is the precision which you get, the absorber, for instance. That's maybe millimeter. Okay? So these are real numbers. I mean, and with this doesn't count the glue, the substrate, the approximation of the material, right? So what is the real accuracy with which we know the density of a given material, how much radiation lengths we are calling? Maybe 1%, maybe less. And then we have a formula which reads 1.0.038. The logarithm of the radiation length that we already know, we may know at 1%. Okay, and we do it in double precision. That thing is double precision, right? 0.038. What's the precision of 0.038? Nothing. It's not real. It's not even 37 or 39. It's just a number. Okay, depends on the material. In reality, depends on the length, because you know that it's not. This is all. The target accuracy of this is maybe percent, but we don't know. And we compute it in double precision. We spent a logarithm computing it with in double precision, maybe 15 order Chebyshev polynomial for something that we know in single precision. So that's why I took it, and I do it to second order logarithm. Nobody has ever seen the difference. I mean, I bet you do. Maybe if you do the dumb test of the simulation of low energy proton crossing 10 micron of gold, for which exists data, maybe you see a difference, but not in a silicon. So why? This is why, of course, Gen 4 will never implement this. Yes.
How much faster or efficient is it to do it in single, like, I don't know, percent, like relational, if you do it with multiple scattering calculation?
That one or this one. Of course, you have learned how to do it. The benchmark, right? Yesterday, so you can try. You take the two formula and you compare. That is huge. What was large? I mean, logarithm in you have seen it. I mean, you go from a logarithm in double precision, which is maybe 50 cycle, from something that is a 1 FMA, so it's 2 cycle. This is written. I mean, I guarantee you that you know perf stat, you've done it, perf record, yeah. Logarithm was high there. You do this, disappear. This full function disappear. You don't see it anymore. This was my job 15 years ago. So this slide is 15 years ago. Okay? So what's your target accuracy? What you do? Another one, this is all anecdotes, sorry, but I promise you not to do anecdotes. You take a paper, famous cash and carp. You type in the cash and carp, you will find the code for this one. Okay? And you will find the code for this famous sentence here, this famous fact. Here, epsilon is the local accuracy required as specified by the user. And SF is a safety factor, often taken to be 0.9. De facto, the first time I looked for this in GitHub, I found 0.8. And then you do all this, and then you compute this quantity, okay? And in GitHub, you will find this 0.9, actually 0.8, step over PO, really PO, of, this is all double precision, huh? Error of epsilon, which is already the number you have said, which is of course 0.1. Times 0.2. Great. You don't want to know how long it takes this. A division. 0.2, the power, another division. All in, okay. Now, there is a magic. You can look at it. Magic approximation of power. When, and in particular, if it's 0.2 is trivial, which will give you the formula. Now, being 0.2 is 1/5. Is this one. By the way, you can also improve it if you want, doing a one round neutron rhapsody. Okay, so you, and it will, at that point it's indistinguishable in float with this computation. And all this to correct a number that we already don't know if it's 0.1 or 0.9, 0.8, it depends on your optimization. Has everybody ever computed this Ruge-Kutta, the 0 point? I've never seen this, made any study trying to optimize this. Maybe somebody works a little bit on apps, but again, it's 0.1 or 0.2, 0.1. Okay. So all the time spent in the function PO for a number, again, removing it, disappear PO, which is again another 50 cycles in double precision, makes it in single precision, goodbye. You can do the Rugen-Kutta in double if you really have, but that calculation, no. So again, what is the target accuracy of all this? And by the way, I was discussing with friend, he says, yes, but at this you have also to add the error of when we do this propagation, how well we know the trajectory, our trajectory, which is going there, because most probably even exceeds all this error and depth, because that's the only propagation, assuming that you know with infinite precision the trajectory, which is not the case, because maybe the error, multiple scattering before, of the momentum of the particle is whatever, 1% or whatever. In any case, lower is the momentum, higher is this error, because it doesn't arrive. If it's a straight line, yeah, Rugen-Kutta, whatever is precise anyhow. So you spend all this time to compute all this with high precision for particle you don't care much, or at least have a resolution of percent, well, almost at 200 MeV, yes. Okay, last bit, which I change it in opportunity for optimization, instead of calling huge mistake in coding. But so, as we said, in any language, including C, the default floating point arithmetic is in double. So you write something guaranteed that it will convert it to double, because you will forget something that you write one 0.5. They are now, these days, sometimes they don't, but really. So any other precision needs to be explicitly stated. If you have doubt, you can, this I think is not a W extra, it's not W. You can switch on -W double promotion, and he will tell you each time he takes a floating point and he converts it to double. Okay? We can make an example and see. I mean, the first time you write it, you can see in the assembler, it says, why is it in double precision? Because you forgot 0.5 in the multiplication. C and C++ by default will never reorder or transform expression if the result may change. So if you write A plus B plus C, you will do A plus B and followed by C. This is not the case in Fortran. Fortran is formula translation. So he pretends to know what you want. Okay, which maybe is good. We'll discuss this. Okay. FMA, I say, is an exception. They will say no because you explicitly asked for it. But you don't. You just say, please compile this for a target supported FMA. And the default is, what is this? Compression is not. Is on. Okay? Remember that no matter what they say about C++ and the very latest standard, C is a language born in the late 70s. And in particular, GCC is bound to compile correctly the code of that time and not to break undefined behavior or not, because people will become mad. So expect usually the compiler to compile your code as it was written in the late 70s. Okay? So you normally compile with -02, which, or 03, it means that the compiler will stay away from your floating point and will respect almost all. But it will also respect some funny late 70 obligation of the C language, like, for instance, the error flag. Whoever has tested the libc error flag after square root? Erno. Do you know Erno? Has everybody ever seen R and O? Of course not. Nobody uses. All right? So, but the code has to respect this. Okay? So when you, and we can see it in Godboard, that when you write square root or any other code to the function, including, you will see these funny things that he computes the square root and then says, if it's negative, actually it's not, if it's none, then recompute the square root to use calling a square t. And in the old days, this was in line exactly where the square root was called. Because he has to emit this error flag, which is statically, is not even thread safe. No, but he has to respect it. So just put minor f no mat r no, please. Okay. The other one, and this I think is default on GCC, is the trapping mat. Again, yes, it will maybe emit this IEEE exception. Nobody traps it. Sometimes we have code, we look at it, we try to trap. Yes, it could be useful if you really want to know. But there are other instrumentation methods than this in order to find if you have a none. If you want to know where the none originates, then this is useful. But otherwise, you just ignore it. Okay. In any case, you have to rebuild something. Okay. So, but and trap the exception can be done. I think we did it because sometimes you really want to know where the none occur. But if not, these are safe. Then we start to something which is a little bit unsafe. You can ask, not sign 0. So I just assume that the user do not distinguish the sign of 0, which, as I said, most of the cases is the same. And this already start to get more optimization done, because sometimes you ask the compiler, sorry, why this is not optimized? Ah, because it could be -0, not 0. Okay. And then comes the more tricky one, which is finite math. So you assume that the code does not emit none and if, which doesn't mean it will not do it. Okay, but that you say, look, normally will not emit, because if it emits a none or an if, you are doomed anyhow. Right? So yes, it's nice to know, but you know, it will. So what? I mean, the only thing which doesn't work is none, because it's implemented as x not equal x. Fine, I can implement easier. Is none just looking to the exponent, and if the exponent is all 1, then it's either infinite, so I can trap it much simpler than just x. And of course, the comparison with the none is always false. So if you compare x with the y and any other, is none. And this makes also, for instance, and this will in any case, for instance, break the sorting. Okay? So if you have numbers and then you have a none, the probability that the sort will go in infinite loop is 1, because it will say x less than y, false. Okay, y less than x, false. And it will go in infinite loop. If you say finite, no, because none is largest than inf. And minus none is smaller than minus inf. And so the sorting will work, and all the none will go at the fur, and then you clean it. So you have in any case to, if you have a problem with nuns, you in any case have to trap it yourself. And you can trap it using a proper is none, which is not the standard is none, looking to the S. And then you remove it. You have to do something, because there are things which don't break, because none propagates. So you can propagate. If you have matrix multiplication, whatever, the none, yeah, everything will become none. It doesn't matter. The important is not that you get a none each second matrix multiplication. Then you have a serious problem, right? You have to fix something. But if the none happens 10 to the once each, God knows when, okay? And then you trap it at the end and say, oh, none, I have a problem. I have to change algorithm. I have to do something, okay? Or before a sorting, well, better I check that I don't have none, because it will break anyhow. Finite math or without finite math. No, without binary math. With the finite math only, at least the sorting will not break, and will put all the none at the end, and then you clean up. Anyhow, this is why it's yellow. And then there is the red one, because the code will start not to work anymore as it's supposed to be. So associative map, it will free order according to him. So, but this is useful if you write things x plus y plus z, and then a little bit below this written z plus x plus y. In this case, they will not reorder. Instead, if you say associative map, it will, x plus y will optimize. So if you expect to write code and then the code optimize, well, associative map will make it optimize. But if you don't, if you not, remember that x plus y plus z is diff, and c plus x plus y will not optimize x plus y. Okay? This is not necessarily what you expect. So if also because you wrote x plus y plus z, not because you knew it, that the precision would make it correct. Right? You just wrote it because you copied from your algorithm written, I don't know how these days you write algorithm on paper. And then reciprocal maths will allow the transformation of the division to use RCP. But also that you do 1 over x, and then somewhere else you do y over x, and then z over x, and so on. He will never write z equal 1 over x and then use multiplication. If you say this, he may do it, because he can also decide now division is fast enough. Okay. But if you have in a code 1 over x somewhere, and then I even not say a over x, b over x, c over x all over, you can say z equal 1 over x and then multiply, because multiplication is up to 6 times faster than division. And then there is fast math, which says all the above. And for a long time, the Intel compiler had by default fast math. And there were people, Atlas, which was using the Intel compiler only because it was by default fast math. Because it says, oh, but people don't know all this. They have to write fast math. And in fact, they introduced this minus O fast in GCC and Clang, and now it's deprecated because they don't like it. Okay? Because also, I think at the end, also the Intel decided, come on. Huh? But I mean, I took people which were using the Intel compiler because the code was faster. And this was just because by default was fast math. But they produced completely different code.
How does this relate to the O2 optimization?
Oh, O2 is only this one, maybe. Okay. Maybe. But it's part of the exercise. Come on, it's part of the exercise. So as I said, the FMA is controlled by this flag, and the default is changed in the last 5 years between, we have seen it was Clang 19 already different, okay? So the contraction by default is should be fast, which means that it will contract anything, but it could be also on, which means it doesn't contract if they are in different statements. This is one of the example I give, and you change the compiler. You see this? Okay, so this you can, as I said, you can in principle write FMA only when you want it. You put it the contraction off, and then you write FMA where you want the FMA to be used. That's and then you control also, as we said, reproducibility. It's reproducible already, because CUDA, yes, it's true, but at least in some old version of CUDA, I saw it that sometimes it does not honor the difference, because because he thinks that it's lower. I mean, I don't. Maybe it was a bug, but okay. But if you write FMA ABC, that's honored. And if it's not supported by the hardware, it will do it in software, which makes it slower. But usually, if you write FMA AB, it will do it. But you have to be, and it will optimize the minus sign if there is an instruction which uses the FMA, where A is not an accumulator, but it's a subtractor. Okay? So this is the typical example that you all know. So if you have A star X plus A star Y, because you wrote it like that, and well, there are two things. Either you wrote it like that because you wanted to compute it like that, which is unlikely, or you wrote it like that because you copied your formula, because it's not A star X plus A star Y, something which is obscurated by your object-oriented C++ object. We see it later. So if you write it in O2, this is old code, sorry, it's in a slide at 10 years old, it will look like this. Now you are used to read this, right? So it's 2 multiplication add, and if you say fast math or any of the other, you see that it first does the sum of that's the sum, and then the multiplication. So it does X plus Y, and then multiplied by A. as you can recognize by the 1 or 2 or 0 in the XMM that you have learned last few days to distinguish immediately which are the argument, and you know which is the input and the output, which I always forget. But I was here when he was telling you, so I think this is the input and that's the output. So destination, source destination, yeah. I don't know, is this Intel syntax or, but there is no pointer, so we don't see the difference. Next slide. So, to close it, what was the author intention? Formula translation, you get again. The first one is energy loss and variance according to Beth-Hettler, as in this paper. And this is how it's written in some obfuscated object-oriented code, which most probably everybody has it. Right? That's it. Now, in order not to obfuscate, you know that mom.mag is just the square root of x squared plus y squared plus z squared. But you don't know, actually, because this is obfuscated. Maybe it's written really pt or magnitude. Man, who knows what the representation? Maybe it's phi r. Forget, this is about, it's a different talk. So let's assume that mom is a little bit, is a structure which is x, y, z, okay? And then this is the code, which is in double precision, God knows why. And, okay, so it's really, so if you do this and you do it only O2, it does exactly what is written. And maybe you recognize that there are many. Yeah, maybe it's true. Maybe he wants to really do the exponent minus 2 times the normalized part and the exponent of the normalized part and the exponent of the minus log, log 2 divided log 3, possibly each time he goes through this line, which is what they would do. Maybe no 3, maybe not. But I don't know, we have to see. You can try with GCC 5, which was the version I suspect I was used at the time, then I rewrote this in an optimized way, or today, okay, where the normalized path is this guy. Well, it's the rack length, the damped radiation length that we know at 1%. Okay, everything is double precision included. Okay, besides that, and all in double precision. So there is a large amount of possible opportunity for optimization. Or this code again, which is again real code from CMS, where you say, well, this is the PT, which is of course mom.perp, which by the way is the same. Oh, it's not mag because it's x squared plus y squared. And then what you do with the PT? Oh, you divide by PT star PT, yeah. You first take a square root, and the first things you do, you multiply it. Okay. And then you continue to do PT star PT divided. And as I told you, he will respect that. So he will really do 1, 2, 3 division by PT star PT. Maybe you'll optimize this. Okay, fine, I gave you that. But he will never optimize the square root and the PT. And the 3 times he will do the division, because you told it to do the division, not the multiplication by 1 over. Okay, so you just already take this code, you put it in Goldwater with some proper additional little bit in order that mom.x you remove it, x, y, z is enough. And you put something around, the compiles, and then try to see with various variation how much the compiler would do it, optimize. Surely in Fortran would do it immediately, in C++ maybe, and then you write it by hand at the end of the optimization, because you can try with different compiler, you discover that it's different between GCC 19 and Clang with 22, whatever. I don't want to comment about again this wonderful pt square divided square root. Okay, so you can optimize it in many ways, and yeah, this exercise is to take this and optimize yourself. After all, was my work for several months. I made a career in finding this code and rewriting and making disappear out of perf. So that's good. It's finished. It's finished because we don't go through the additional material. I mean, yeah, but it's interesting. You know, why 8-bit is enough? Yeah, as I told you, if you have a electromagnetic calorimeter, come on, you don't need, you just need integer. Okay, that's a different talk if you want to do it. Okay, questions, comments. I stay till 4:30 at least because they don't open the door to go to France before, so it's useless. If I go out now or at 4:30, I will arrive home at the same time. Okay. So as I said, so here the exercise is not written what is it for this part, because it's just you take any code or the one I propose, and then you change the compiler option and see what happens. To see the code, I mean, there are funny things like you write a square. I think there are, I don't know what I have here. Because then I write this Godbolt, you know, this Godbolt 1 month ago, then I forgot. So, oh yeah, these are our kernels. Oh, these are, yeah. So these are the kernels. So this is really the simplest things. If, oh no. Don't do this. Okay. Okay, so these are the usual this is, you have seen it. So here where you don't see it, okay. Oh, this is with the I think this is with the fast math. So the first things you do is that you remove fast math. Hopla. Doesn't change much. And then, as I said, the fun, so you see that you continue to see the FMA, but that's because it's native. Which usually you shouldn't, I don't know what means native here, of course. Huh? In fact, they say don't use native. You have to use x86 minus 64 minus v4. Okay? But you can use without FMA. This is without FMA. Right. Minus v4. Then here you can change the contraction. But you can do something funny. You see, this is in two statements. I can do, but then we lose a bit of things. Okay. You see, this is in two statements. And then we go here. I did it before. Some of you were here. And you go clang. I don't remember, was already the last clang? Let's see. Because the last clang is on the side, I think. You do clang 12. What else? Oh yeah, it doesn't support the thing, so okay. Clang 12 is too old. Why? Select a compile. I'm trying to, because okay, so let's see, clang 21. Yeah, you see? Doesn't use FMA because there's a different default for the contraction. So if it's in two statement, it will not contract. Okay, and then you can change you can change compile, you can change the various things. I don't have the square root here. The square root, maybe I have to change. It's complicated to type and look here. So it's more the typing error that this is far. Oh, well, okay. Doesn't matter. So what do you, once I managed to make it compile, what do you expect this stupid things which is called, well, okay, it's only the name of my file. Okay, oh, wonderful. This is the problem. We say, oh, we do some easy. Each time you type, there is a mistake, include Sima. Okay. Wow. That's a square root. Now, first of all, you notice, oops, he has converted to double precision. Oh, great. He has converted in double precision for 2 reasons. Then he makes, oh, a commiss. Why the hell he does a commiss? He has a zeroth. Yes, a zeroth is done a big salt. Huh? Yeah, but where is the square root? Because the square root is here. And yeah, but the commiss is, if it's negative. Okay. So, yes, if it's negative, because this is new code, so it's not in line anymore. At least the front end will not parse the useless code before reaching the double precision. Okay, but there is to jump, so it checks. Oops. First of all, I converted to double. After all, you ask for square root, not square root of f. So it's in double. The default is double. Then I say, oh, it's negative. Oh, if it's negative, then I go and I do, I call the square root somewhere. Yeah, I call the square root. All right. Otherwise, I do the square root, and then I jump because I have to do the division and then convert back to float. Great. So first of all, we write 1.f, and here we say std dot. Vroom. Everything now is in single precision, at least. But he continues to do all this thing, okay? Now, the problem is that the machine has to decode all these instructions. And there is a limit on the number of instructions that can go, into the cache of instruction. So if it becomes bigger and bigger and bigger, then it will go beyond at some point, and then you start to pay the price. I mean, it's not that, oh, it's just a jump that's always a jump. And second, he has to do the commiss. Now, it will not cost, but if it's in the cache of instruction, if he has to decode it, he has to decode it. I mean, okay, so you go there, and now we start to say, look, I put O fast, okay? Well, O fat not, but O fast. Yeah. Okay, it's gone, everything is gone. So, first of all, inverse square root. You remember the inverse square root. You say, where is this 2? What is this? The one round of Newton-Raphson iteration. And finished. That's it, right? So it does and then this is the one round of Newton-Raphson iteration. Looks a little bit Yeah, but this is it. It looks to me that there is one multiplication too much, but it's 1.5 the Newton. Yeah, because it's 1.5 plus 0.5 the Newton-Raphson iteration. If you read it, yeah, you can decode it. The constant are somewhere down. He has to read it from memory, right? You will find something. Yes.
I have a question back to the momentum example.
Yeah.
I'm actually quite familiar with the stuff. So in a like real world code example or like environment when you're like daily working.
Yeah.
Like, of course you can try to optimize as much as you can, but there are like other constraints, like the professor saying, why not fast enough? And I don't get that you make your code like 2% faster. So,
but that's his problem. In fact, we used to quote the amount. He uses the carrots. We use dollars. Okay, because if you are an banana, sorry. If you have an experiment like CMS, Atlas, LHCb, or whatever, you do computing, massive amount of computing, and usually people arrive with a budget. Okay, which is, say, 1 million euros per year. And 1% or 1 million is not a lot, but is of the order of the salary of a student for 1 year. So having a student optimizing the software for 2% for the whole production on a big data experiment is a saving, theoretical saving, which is larger than his salary. This is how I count. But I usually say this. So my time has been properly spent because we save more than my salary. So for the next 2 weeks, I can take holiday because this is done. I did what I was used to do. Now, it's true. This is true. It's true. It's not true. It's not really true. Most of the time we waste is because not of the floating point. It's correct. We are often 50%, 25% occupation of the machine for other reasons, typically because data don't arrive, or because we have to parse Python for 2 minutes for a job which takes 10 seconds. This is another story. But
kind of like where I want to go.
So that's the motivation.
Like, it could be that this part of the code is then a bit faster, but in principle compared to the rest,
yeah, but
it might be still irrelevant. And
negligible, but this depends what is negligible. As I said, 1% in total. If it is your little routine, which is already 1% of the total, you optimize only 1%, maybe it's negligible. But if it's a tracking code, which already by itself is 80% of the total, and you optimize by 10%, that's huge. Okay? No, you are perfectly right. You have to see, but many optimizations are not worth. And often you don't really know in advance if it's worth or not.
Yeah, now to come to my actual questions. Like, you gave us some examples of stuff that might be costly.
Yeah.
But are there like other things that we should be very careful about that are
in floating points or in general? Because in principle, in general, there should be other lectures which tell you, but I already told you two, the main two, which is the what is called the front-end latency and the memory bandwidth, which goes back in the back end. So the latency of the front end is due to the decoding of instructions, which means usually or code bloat. You've seen it, an example of code bloat, because he has to parse 20, 30 lines of code. And this is easy. For instance, with my little example of inversion of Kalman. At some point, there are too many instructions to enter into the cache, and then the code suddenly explodes of a factor 10 or more in speed, going from 5 to 6 dimensions. But that's maybe today. The next machine, they will increase the size of the cache and will not happen anymore. And then is, of course, the front end, which is dominated by the if. In C++, so, and by the condition code and by the bad predicted branches, okay? And most of the bad predicted branches comes from virtual functions which cannot be predicted. So this is the famous, this is again another talk, which is called obfuscation, the famous virtual int, okay? So you know that the first things you learn in object-oriented code, that the code should be generic, any function should be virtual and possibly written in a not inlined. So you have a virtual x return, virtual x return underscore x, virtual. So this is a virtual function. Virtual function goes through a table, and the code doesn't matter. And usually, if the code predicts correctly, now it's okay. But if it doesn't predict correctly, because you have, for instance, if one case is, because if you have two virtual functions of two different objects with the same base, and you alternate between two-dimensional x and three-dimensional x, but both of them return x, but the compiler, no, the compiler cannot see it, in any case cannot do anything, because you can always, because you have a base class, and you can always derive, unless it's not final, okay, it will always think of that it goes through the virtual base, always go through the virtual. And if you alternate two different functions, which happen to be in different addresses, these two functions, it will always get it wrong. If they are in the same location, it learns now. And in fact, this is well known that suddenly, 10 years ago, 15 years ago, going from Harlem to Broadwell, so really old stuff, suddenly the Atlas code got 15% faster because they had this access to the free cheat through virtual table. And because of Python and not because of C++, eventually Intel discovered that it was better to have a faster and more clever branch predictor, because Python is all branches. So they learned how to see patterns. So the hardware is really clever. It's better than AI. It looks to your pattern and see the ifs. He counts. He has a counter. And he sees that this is more often going there instead of there. Okay? And so he does the prediction. He really do speculation. Okay? And he goes maybe 20 instructions before yours. But if it's the wrong one, he will go, he has to clean all this, destroy it, and it's what, 200, 300? So this is a typical source. So a typical source of problems is if you have useless, in C++ is typically, so if you have useless branch, which typically in C++ is useless virtual functions, remove it. Remove it. You don't do algebra with the virtual function. You just, this was the example we saw before, right? I mean, this, when I say obfuscation, you don't know this perp, what is, okay? And it could be a virtual function. I mean, in the 80s was a virtual function, and depending if it was implemented as XYZ or PT phi eta, it was giving the 2. This is, and then say, oh, but my code is the C++ is other times lower than 4. Yes, of course, if you obfuscate the code, how you want the compiler to know that this one is just the square root of x. But you don't know. Okay, but besides that, so that one is the first source. Okay, so any branch which in particular produce wrongly predicted branches is a problem. The other one is memory access. So this is again X, Y, Z. So my typical example is take a class with a 15 member, and in the middle you put a Boolean. Then you write a vector of this class, 1,000 of them, or 10,000 of them, and then make all the Boolean false. So you know that as we were discussing, the memory is loaded by cache lines, right? So by whatever is number of bytes, 96 bytes, it reads each time. Okay, so if you have, you have done house versus soy yesterday or the day before, you have discussed this, right? So if you have a class X, Y, Z, Boolean, it will read all of them in memory. And you use only the Boolean. And then you go to the next one, another full cache lines. So you enter and besides, and even worse, these are allocated on the heap, each of them, and accessed through a virtual table. Okay? We are talking maybe of 1,000 times slower than if you have an array of Boolean. Yeah, imagine, these are randomly allocated on the memory because, you have done with the new, not in a vector. So you have a vector of pointers, the famous, how do I call this? This is heterogeneous vectors. Polymorphic, great polymorphic vector, always happens. Even CMS with the its, because it can be 1 dimension, 3 dimension, whatever. And you have the shape, the famous example of the shape, the square, the circle, the thing, and then the color. You put it all together. Also the color, right? Everything. So you have a class which is what could be this equivalent 20 double with all these things, and then allocated on the heap at random because you created and deleted on the random each time he enters into your game. In fact, the game people were the first to complain about house and so on. And you have all this allocated at random, and you have on an old machine which has not yet learned patterns. So you read, and then you ask again, and the prefetcher becomes mad because one is here, the other one is after 10 bytes, and the other is after in a different page, and he has also to recover the page from the virtual system. So again, what we are talking about, and instead of all this, you write a wonderful little array with only the color or the Boolean, and factor again is 1,000. This is my typical example, which I went again on obfuscation. Okay. So these are the reality, the floating point. Once you have solved all that, you will see the log. But before, I mean, we were going, so malloc, we managed to do 20,000 malloc per second only because you cannot do more. I mean, you have, the first things is not to be limited by malloc. So if malloc in your perf stat is the first, okay, work until it goes down to the 50 or whatever. It's very easy. Yeah? You wait 6 months, you redo it, malloc first. Fuck. Okay? So malloc is your first to remove. Once the malloc is gone, most probably you have also solved some of this. Then you have to work on all these stupid virtual pointers and mispredicted branches. And then on the bandwidth, which usually means throw away this poly-head classes which contains the location, the whatever, the pointers, the color, and the boolean, and you don't know what more, and just put it as a house or at least little structure. Make sure that if you load the cache line, you use not say all of them, possibly all of them, but not just one. Okay, so a float 16 for an entire cache line. So it's very, these are the real problems. This is a different course. This one comes to the end. Once you have solved all these other problems, then you will start to see your log. When the log becomes in the first 10 of your perf record, then it's time to remove the log or the po. But he came pretty fast, I would say this, because, and I hope that, yeah, I'm thinking, oh, but when they have architecture, 3 weeks, you will discuss all these things, maybe not how C++ can generate all that, maybe yes, but or maybe they assume that you already allocate all the memory once in memory, like in old good Fortran common blocks. And also in C, I mean, if you say, what? Why you are doing all this? You just allocate to gigabyte of memory and you work there. Yes, yes, but no, I mean, you want readable code, not pointer in, well, say, oh yes, but it's the allocator. I know, I mean, Bjorn, we just say, oh, that's not a language problem, it's a library problem. We provided allocators. You that you are not, you don't know how to use or how to write an allocator. Say, yes, but I mean, new. Delete. Very interesting problem. I mean, I can give you a course of another day on that, but it was not supposed to be on this. So here we say, well, if you arrive to the point where the floating points are, or arithmetic is your problem, either because of precision, and I tell you, I mean, really on GPU, you want to go to float. Okay, there is this interesting thing. So how could be that they manage to reach the moon using Kalman filter in 1969, and we systematically segfault if you use floating point, single precision floating point, doing tracking in our detector? Well, because we forgot all the details of doing properly things and just optimize when it's needed. And so now everybody's running to single precision because of GPUs, and they eat the places where you need a little bit more clever than just doing formula translation. After all, this is not bad. It produces correct code. And you have to write it like this. By the way, you have to take the formula and write it as it is. Then you optimize, and then you write your test, and you check the accuracy, not the precision. Okay? And if the accuracy is below your target accuracy, which you do statistically, I mean, there is plenty of way of doing it. I can, depending, I don't know if you are a high energy physicist or climatologist or whatever, but everybody has his own piece of code to do statistical or bitwise precision. And if you are happy, then you optimize it. But as you said before arriving, these things to eat your code, there is most probably years of optimization to be done each 6 months. This is because people keep adding code. Yeah. More, as I said, we will add solutions beginning of next week, so you can play with these various things. You can try by yourself. I can show you the Taylor if you, I think, where I have it, the Taylor. Maybe I can find, I mean, only because it's fun. Because it's in, because it's in Dubai. because it's in NumPy. Yes, yes, yes. Yeah. Yeah, no, they are. You are free to go.
Okay, then officially, thanks Vincenzo.
Yeah, it was finished since 10.
Those who want to go, free to go. Vincenzo will stay 10 more minutes, he said.
At least. Okay, so this is a Taylor expansion of sine
Have a nice
x,
weekend.
okay, in from 1 to power 8. As you notice, I just put the factorial together with z. This is called Horner expansion, using this kind of coding, so that I don't do x to the 7 over 15 factorial. But you notice that this is z squared, by the way. The sine is, of course, 1 plus x squared over 3, right? And over 6, sorry. Okay, so this, okay, and then you continue. But so this is here. I don't even up to 110. I multiplied, and then I solved. Okay, and it's written in Python, so you can run it trivially. Python 3. And of course, I mistyped. And voila. And you see the table maker problem. You see,